Hello, everybody. Welcome back to the second day of Cisco Quantum Summit. After a very exciting and really interesting first day that was focused on using quantum network to scale up quantum computers, now we are coming to the second day where we focus how a quantum network can help and support classical application and use cases. My name is Reza Nejavati and I lead quantum research in Cisco. So without further ado, we move on to a very quick overview of agenda. We start with a keynote from one of the Cisco fellows, and then we move on to our academic session that we have 4 talks from various universities across Europe and US. And then we, after that, we have a presentation by Cisco research and engineering team that they show 2 of the use cases that we implemented using quantum network to support classical application. And then finally, we conclude the day with the industrial session, which we have a talk from 3 industries and 1 talk from the Oak Ridge National Lab. And then we have a panel after that. So with that, I would like to kick a start and invite our keynote speakers. So we have Ramana Kompella. He's a Cisco fellow and also head of research in Cisco. His organization is Cisco Support Research on AI, cybersecurity, distributed system, and quantum. Prior to joining Cisco, he had a successful startup, and also prior to that, he was an academic in Purdue University. He has a large number of the peer-reviewed publications and patents. Ramana, the floor is yours. Please share your screen.
Thank you, Reza, for the kind introduction. And let me. All right. After an exciting yesterday, I'm super excited to kickstart this day 2 of the Cisco Quantum Summit. So as Reza mentioned, my name is Ramana Kompella. I lead Cisco Research, where I have the privilege of leading a team of world-class researchers that conduct research in many areas of emerging and strategic interest to Cisco. And we advance the state of the art along many directions, such as networking, AI, ML, cybersecurity, and of course, topic du jour, quantum. And we collaborate a lot with academic researchers and faculty members. We publish more than 100 plus papers a year in many top conferences and journals, and of course, co-authored with many of our collaborators. And the Cisco Quantum Labs, headed by Reza, is part of the Cisco Research umbrella, and definitely there's a lot of collaboration across a broad and diverse team of researchers that span all these different areas, in addition to physicists and optical networking folks in our team. So with that, so I want to kickstart this conversation today by talking about the fact that Cisco is fundamentally a networking and security company. And we have largely helped build the foundations of classical networking technologies that are currently powering the internet. And if you look at classical networking, we have a lot of ways of interconnecting different computers and nodes with wireless access points, terrestrial satellite networks, interconnected by switches, routers, and other networking devices. And in classical networking, you have messages or packets flowing from one node to another node in somewhat of a store and forward manner, where messages are copied, stored in buffers, at each and every switch or a router along the way. They potentially wait for their turn and eventually get forwarded to their destination. So while of course there's many different types of media like free space, wireless, Ethernet on copper, long haul optical fibers, microwave point to point, still largely messages are transmitted at or below the speed of light. So if you look at the 2 key invariants of classical networks, one is that messages cannot be communicated faster than speed of light. Okay. The second invariant is that copying is actually sort of intrinsic to how networks are built. And if you look at like, the switches or routers, they routinely, copy packets in their buffers and all that. So the entire architecture is built on the premise that, like, that copying is inevitable, and you rely on the fact that, like, there's end-to-end encryption to prevent people from making any sense out of the copied information. Okay, so these two are definite invariants that are part and parcel of how modern classical networking technologies operate. Now, as Vijay kind of like in his keynote yesterday talked a little bit about, like, how classical computing is a physics problem. I'd argue classical networking also has a little bit of a physics problem, or more like a limitation that classical mechanics actually provides, or classical physics provides. For the most part, of course, these limitations have not really impeded us in any which way. I mean, we've not really suffered because of these limitations, but what if we can do better? In other words, at least for a few applications, can we bend these assumptions and do better than classical networking? And that's the premise for, the talk today, right? So enter a quantum network. So we ask the question, just like some classically hard problems can fundamentally be sped up by quantum computing, can we actually do better in classical applications if we have a quantum network in our backyard? And the answer seems to be a yes. And let's examine a little bit about why that is the case and what unique properties does a quantum network actually bring to the table to potentially benefit some of the classical applications. Okay, so the first property that is very interesting and somewhat unique to quantum networking is the entanglement property. It really allows two photons or particles to exhibit correlated states even at a distance. That is, you cannot describe the state of one photon, like a spin, polarization, or other properties, without intrinsically describing the state of the other photon. And it doesn't matter how far they are apart, kind of like conjoined twins. The interesting part is that, like I said, it doesn't matter, whether it's actually like, a few nanometers apart or like even kilometers apart, which led Einstein to call this spooky action at a distance. So one caveat here I want to mention is that entanglement is not something you can use to transmit information faster than the speed of light. And that's thanks to the no communication theorem. But correlations are instantaneous, which means if you effectively measure one of the entangled photons, the other one will collapse to the same state. But this particular phenomenon cannot be used to send any correlated or controlled message. But this does not necessarily mean that correlations cannot be taken advantage of, which I will illustrate in the next slide. And the other property of quantum networks is the no cloning theorem, right? So which essentially says it is impossible to create an independent and identical copy of an arbitrary quantum state or an unknown arbitrary quantum state without destroying the original state. Unless, of course, if you're entangled at the beginning, of course, these are correlated, but if you want to transfer or if you want to copy the state into another photon, you can't do that without destroying the original one. And quantum teleportation is clearly that phenomenon where you can transfer state, but that just means that, like, the original state is completely destroyed. Okay, so the question now is basically, as I mentioned, can classical networking really take advantage of the presence of a quantum network, specifically entanglement and no cloning? It turns out, and people have explored this in the past, there are examples like decision coordination and time synchronization that leverage the property of entanglement. And there are applications such as eavesdropper detection, secure position verification that leverage the no cloning theorem and property of quantum mechanics. There are potentially many more. I mean, recently I've seen papers coming out around how entanglement can potentially improve distributed consensus in distributed systems. So there are potentially many different applications that are waiting to be discovered and explored. Okay, so with that, let me come to the setup of this problem called decision coordination. And this is a well-studied problem. I'm just gonna set the context and why it is interesting. Let's say you have Alice and Bob, A and B here, separated by tens of kilometers. The setup is that both A and B have some local observations, but want to make a decision about how to respond to those local observations in a coordinated fashion. Trivially, one solution is to, for A to make a decision and convey that to B or vice versa. And then the other party will use that to determine its own action locally so that both actions are coordinated. But this clearly introduces a delay, T, which is equivalent to at least the propagation delay, or at worst, depending on the amount of buffering that you have, it could be substantially high. Now, this is the speed of the light barrier that we cannot cross in a classical world. And this is what I've been alluding to in the past. If you need to near instantaneously make a decision in a coordinated way, you could rely on some non-sharing strategies, non-message sending strategies, such as perhaps using the same random number or something else. And it turns out they're not as efficient. Now, if you have access to a quantum network, can we do better? Imagine you have access to an entanglement source E, which basically generates an entangled photon pair, and you send one photon to A and the other to B. Now, let's say A wants to make a decision. It actually makes a decision by fusing its local observation of the photon that it has, the one half of the pair, and B does the same, and it uses its other half and also makes a coordinated decision. Because these entangled photons are actually used to make a decision, both A and B converge to almost the same decision, at least most of the time. And this leads to a much higher efficiency compared to the classical methods. And this phenomenon is generally referred to as quantum telepathy. And folks have written papers about it. But it's also maybe more precisely pseudo telepathy, because it doesn't mean that you can actually allow for any faster than speed of light communication or instantaneous transfer of any classical information. So quantum telepathy actually forms the basis for something called the CHSH, or Clauser-Hahn-Shimony-Holt game, that was first conceptualized back in 1969. It's a popular thought experiment in the quantum world to illustrate the power of entanglement. And this game, it turns out, actually performs much better than any of the classical counterparts. In particular, it offers like an 85.7% winning probability compared to any other classical strategy, which peaks at 75%. Now, there are other games such as the Magic Square game or the Mermin GHZ game, where the quantum telepathy has been shown to offer much higher winning probability compared to their classical counterparts. And many of these games have formed the basis for several trading and fintech applications that are of interest to the whole fintech industry. Of course, there's a fairly more elaborate coverage of this phenomenon later in the day with Ineeth and team showcasing how this setup can be simulated in our Q&DK. And some of the detailed levels of modeling support that we have to better illustrate this particular use case. Okay, so the next application that I wanted to talk about is the eavesdropper detection. And the key intuition here is to leverage the no cloning theorem. Suppose we want to detect the presence of an eavesdropper in the middle of a long haul optical fiber link. And this could be to mainly detect the presence of what is known as a harvest now decrypt later attack, or HNDL, which is one of the most worrisome threat vectors for the whole post-quantum threats to classical infrastructure. So the idea is that, and this is somewhat interesting, and this is an irony a little bit of the quantum phenomenon, right? On the one hand, the advent of a quantum computer is putting the classical security at risk, but on the other hand, we can leverage quantum to protect these links against these HNDL style attacks. So the idea is to actually use quantum signals, and in particular no cloning, where we transmit one half of the quantum entangled pair, okay, to the other half while we measure the first half locally. And the transmitter and the receiver then exchange the measured signals. And a high occurrence of similarity between the measurements at the transmitter and the receiver side clearly indicates that the line has not been tampered with. Even a small amount of photon loss due to some eavesdropper in the middle actively siphoning photons will disturb this entanglement and cause a dip in the rate of coincidence between these measurements. Now, the attacker could be sophisticated and masquerade the loss by potentially siphoning photons, but also re-injecting photons. But because of the no cloning theorem, obviously you can't inject photons that are entangled with the source. And that's an amazing property that can be leveraged to detect the presence of these eavesdropper. Now, this is also particularly interesting and impactful since we have millions of kilometers of fiber infrastructure, and if we can really use this or leverage this to make them secure, that would be a serious game changer. Now, while the previous two examples clearly indicate how quantum properties and quantum networks can be taken advantage of in classical use cases, there are several other things, like the ultra-precise time synchronization and secure position verification that can take advantage of these quantum networks. I believe we have some talks around SPV later, in the day as well. Now, as Vijay mentioned, we are building a unified quantum network that basically covers a wide range of applications, right? Like I talked about the classical, and yesterday, we had discussions around distributed quantum computing, but which requires a quantum network at a local data center scale. But we can also use quantum networks to interconnect these different data centers and also extend it to all the way, things like distributed sensing that require a quantum internet, if you will. And at Cisco, we've been really, building out a common stack of protocols like entanglement distribution protocols, quantum measurement, entanglement swapping, teleportation, on top of which both your classical applications, which are to the top left, and your quantum applications, which are on the right, are all basically built on top of. Now, yesterday we have demonstrated the network-aware distributed quantum computing compiler, and today we have a couple of demos around the two applications that I mentioned. And our framework also, of course, involves hardware, and we have test beds that are basically working with real hardware, and we also our QNDK actually includes simulated and emulated devices so that we can make faster progress on applications and protocols. So with regards to hardware, we've already announced our entanglement chip back in May that generates upwards of 200 million entangled photons or photon pairs per second at high fidelity. And we are also working on other components as we speak, and we'll be talking about some of the updates around these areas soon. Please stay tuned. Okay, so before I conclude, I want to drive this point home once again. Well, it's a bit more obvious that a quantum network is obviously required for quantum applications like quantum computing and distributed quantum computing, where you're interconnecting different quantum processors so that you can distribute your quantum computing algorithm. I feel it's a little bit less obvious and appreciated that perhaps a quantum network can bring some unique physics bending or classical physics bending capabilities to a classical application. We should consider giving a serious look at what other applications can really benefit from the presence of such a network. Until now, this was somewhat outside the realm of practicality, and hence probably very few people have actually paid attention to this. But as quantum networking is gaining maturity and traction and mainstream acceptance, we really need to take a double take here and figure out what exactly are those applications that can benefit from the presence of the quantum network. And I also think this would be a big catalyst to the more immediate deployment of quantum networking technologies compared to, of course, the longer term vision of building a quantum network for real quantum applications. With that, I'd like to end my talk. Thank you for tuning in on day 2 of the event today. And I'm really looking forward to some amazing talks, especially around the topic of quantum networks for classical applications. Over to you, Reza.
Thank you, Ramana. We are running behind the schedule, so I will leave the question for the panel for you. We swiftly move to our next speaker. Is Professor Lian Jian from University of Chicago. Lian is a professor in School of Molecular Engineering, University of Chicago. Prior to University of Chicago, he was in Yale University, and his research focuses on quantum control and error correction and building large-scale quantum systems. Jian holds a fellowship of the American Physical Society, and also he is a recipient of the fellowship from Packard Foundation, and also Laurent Bennett Award from APS. With that introduction, Lian, floor is yours.
Thank you, Reza. Yeah, hi everyone, and good morning. And it's a great pleasure to have the opportunity to talk about our recent research on this vacuum beam guide, which will be a new way to achieve large-scale quantum network, and also discuss about the applications. Yeah, so this is a joint collaboration with people from Chicago, Pittsburgh, Stanford, and Caltech. Yeah, so as we all know, one of the major challenges in building a large-scale quantum network is the attenuation in our optical communication channel. For example, in the fiber channel, the typical attenuation length is about 20 kilometers. So if we go to 1,000 kilometer scale, even if you can send our photons at individual photons at the rate of 10 to the 12 photons per second, ultimately we probably will not even release photon even after waiting for a year. So that kind of poses a challenge because of the quantum communication channel attenuation. And to overcome this challenge, actually, currently people are mostly pursuing two approaches. One is the satellite-based quantum link. And the advantage is actually to use the vacuum in the outer space so that you can send the photon over long distances. However, the challenge is limited bandwidth, and it depends on the weather, and also it's very expensive to launch many satellites. So the second approach is this ground-based approach, which is quantum repeaters. So it will be compatible with the existing fiber network, and hopefully will be more reliable. And the challenge is actually it takes non-trivial efforts to do entanglement swapping while maintaining high fidelity, and need additional quantum operations, quantum memories, as well as the classical communication if you want to do a two-way entanglement distillation. So both of the schemes I think are currently actively pursued and are both promising. And on the other hand, we're also thinking about new ways to achieve long-distance quantum communication. So one inspiration that comes from this recent development of this laser interferometer gravitational wave observatory, LIGO, which kind of detects the gravitational wave events in 2016 and got a Nobel Prize in 2017. So if you look at the design of the LIGO device, it is actually a L-shaped microsync interferometer. And each of the arm of the microsync interferometer is actually a fabric probe cavity, which has a length of 4 kilometers with a thickness over a few hundred. So if you calculate the effective attenuation length, which is how far the photon can propagate before it gets absorbed, actually it can propagate over 1,000 kilometers before being absorbed. So that indicates that it's actually possible to bring the vacuum to the ground, and we can also still propagate photons over thousands of kilometers. So inspired by this gravitational wave detectors, we actually proposed a new design or new approach to achieve long-distance quantum communication, which we call the vacuum beam guide. So this is actually a ground-based vacuum enclosure, which kind of insulate our a quantum communication channel from outer environment. So by reducing the air or medium absorption, basically what we need is an intermediate vacuum at the level of 1 Pascal. We can reduce the air absorption by 4 orders of magnitude so that the air absorption is not a dominant loss mechanism. And moreover, we carefully designed the optical elements so that the length we use to focus the beam of every few kilometers, it will only introduce less than 10 to minus 4 per optical element. So the goal is actually to build an effective low loss channel, which hopefully can be highly transparent, so that the effective attenuation, which combines the loss from the length, the gas, and the alignment errors, that is less than 10 to the minus 4 dB per kilometer. So there are some of the design parameters in terms of the separation, which is a few kilometers, and you can design the AR coding so that it works well for wavelengths around telecom, and also the beam waist is about a few centimeters. So with these design parameters, we claim it's actually possible to achieve an effective attenuation less than 10 to the minus 4. So let's look into the key contributions of these different effective attenuation terms. So first is the attenuation due to the length that we introduced to focus the beam. So instead of having this optical fiber, which is kind of self-focusing the beams, we actually just put the lens every few kilometers. So that will minimize the material loss. But whenever we put the lens, there could be effects from some of the finite size of the lens. We might lose outer part of the beam by increasing the radius of the lens from a few centimeter to about 20 centimeter, compared to which is much larger compared to the beam waist of 3 centimeter. We are able to minimize that additional finite size loss. So ultimately, what the loss is actually limited by the anti-reflective coating of our lens. So we can push it down to the level of 10 to the minus 4 or even lower for each lens, so that we can get an effective attenuation less than 10 to minus 4 kilometer for the lens component. Now, the other contribution is the gas absorbing due to the gas. And we can just reduce the air pressure to less than 1 Pascal, which is less than 4 the magnitude of the air pressure, at 1 atmosphere. So in this way, we can minimize and essentially make the gas loss negligible. The third contribution is the alignment, because our vacuum bag will be based on the ground, and the seismic motion or other motions in the air might affect the alignment. So in this way, we actually need alignment to be less than 1% of the beam waist. So basically, if we target choosing the alignment to be better than 0.1 millimeter, which is actually feasible with the current systems, we can make sure the alignment loss is also below the requirement. Yeah, so therefore, we can show that the total loss can be less than 10 to the minus 4 dB per kilometer, which is more than 3 orders of magnitude better compared to the state-of-the-art optical fiber. So ultimately, we show that actually it's possible, and based on our design parameters, to achieve ultra-low attenuation, which is less than 10 to the minus 4 dB per kilometer, compared to the fiber, which is about 0.1 dB per kilometer. So overall, we can achieve 1,000 times more transparent in our vacuum beam guide compared to optical fiber. And this is actually sufficient to achieve a global, or at least a continental scale, or even global scale quantum communication. So besides the highly transparent channel, you can see also this channel is also transparent over a wide optical window. So it can span over about 5% of the optical wavelength, which means that actually you can achieve a communication over this about 10 terahertz kind of frequency window. And we actually compute the quantum channel capacity as a function of the total distance. And here we show like 3 different curves associated with the stabilization that we can achieve at 1 millimeter scale, 0.1 millimeter scale, or the ideal. We see that once we can stabilize the length to the level of a 0.1 millimeter, which is achievable with the current active stabilization technology, we can send information over long distances, well beyond 1,000 or even 10,000 kilometers at a rate of 10 to the 13 qubits per second. With this number is actually comparable to the current optical communication, which shows that actually like with the fiber, so which shows that we can actually like send a lot of entanglement over this vacuum beam guide channel. So another way of saying it is, if we can build a vacuum beam guide and we can send the photons through, in principle, we can generate a lot of entanglement, and the entanglement is probably more than enough, more than like what we really need current quantum applications. So with the vacuum beam guide, we imagine we will have a hierarchical architecture for our future large-scale quantum network. For example, we can use a vacuum beam guide as a main like trunk line for kind of sending large amount of information between different local stations. And then the local station can use the fiber links to distribute over like individual users. So in this hierarchical structure, we can kind of make it cost effective while still maintain a high quality service with a high bandwidth over long distances. So now in terms of like the applications, we imagine that, okay, potentially the vacuum beam guide can not only be used for these like large distance communication, it can also be used for other quantum applications. So one application is actually it can be used as a optical quantum memory, because there is no conversion required to convert from photon to other modes for storage. You can directly use these vacuum beam guides, and just by like using classical switches or mechanical switches to switch these optical signal photons into the loop of the vacuum beam guide, and you can store these photons for 50 milliseconds or even longer. So that shows that actually this potentially could be a good optical quantum memory. And since we have high communication, high bandwidth, in principle, this quantum memory also store a lot of bits of quantum information. And the second application is that these vacuum beam guides can also be useful for device-independent quantum key distribution. Because of the high transparency, you can communicate over like thousands of kilometers with a loss less than 10%. And with such a low loss, in principle, you can use that to demonstrate the violations of the Bell's inequality, like the CHSH inequality, which has a threshold value about like 2/3. So if you can communicate photons with the efficiency better than 2/3, so in principle, you can demonstrate violation of CHS inequality. And with that, you can also use it for the demonstration of device-independent quantum key distribution, so that you can generate secret keys without relying on the additional assumption of your physical hardware, and you can get a security of the security of the key as long as it violates something like the CHS inequality. And the third application is actually we can use these vacuum beam guides for long distance, large distributed quantum sensing. One application is this long baseline quantum telescope. As we know that actually the precision of a telescope will, for example, the angular resolution you can achieve for a telescope scale inversely with the separation between the telescope stations. So if you can separate the telescope stations at a larger scale, like thousands of kilometers, and connect them with a vacuum beam guide, and also like interfere photons from remote telescope stations transmitted over this vacuum beam guide, you can build like quantum interferometers, so that you can build like a long baseline optical telescope. So in principle, one can achieve like ultra high angular precision in the optical domain, which is important to explore like to find more planets, or even like detect like other astronomical signals. And one of the exciting application which kind of like emerged, also mentioned in the previous talk, is actually we can use this for coordinated decision via quantum telepathy. So quantum telepathy can enable two non-communicating parties to coordinate their behavior, which is impossible to achieve using classical mechanics. For example, the well-known example, which also got the Nobel Prize, is a violation of CHSH-Gauss inequality, which you can translate it as an XOR game, which you can think it as just a utility function where the two local players, they get their local inputs and they need to make some like local decisions. But turns out that with the quantum entanglement, you can achieve a better performance because of the statistics enabled by quantum mechanics to outperform every possibility is allowed by classical in the classical world. So using these quantum resources, we also recently proposed that you can generate using entanglement shared between local financial centers, which can separate it by tens or even hundreds of kilometers, then so that they can make a better decision and potentially get kind of a better coordinated decision making, achieve better performance in some non-local games. So finally, let me just summarize that our vacuum beam guide, we believe it will be a new approach that allows us to generate entanglement over long distance by providing a highly transparent channel with attenuation length over 10,000 kilometers or better, and also achieve a communication bandwidth of order that allows us to communicate over tens of teraqubits per second. And this has opened up the applications, including building new quantum memory, quantum cryptography, distributed sensing, coordinated decision making, as well as the blind quantum computing, which is also an exciting application. And thank you for your attention.
Thanks, Leon. We have a couple of questions from audience. Is that one of the first question is that does the segment between the two lenses need to be line of sight, or
could you repeat the question?
Yes. The question is that does the distance between the segment needs to be a line of sight or can be bended?
Yeah, so here by design, we assume it's vacuum in the middle. So it will propagate as what the Gaussian beam would propagate. And if they are further apart, one way is to put a mirror so that you can kind of reflect the beam a bit and then you can focus again. Yeah.
So another question is that how the capex and opex of this system of VBG compares with the satellite system?
Yeah. So in terms of the communication, the bandwidth, this is actually the VBG can be orders of magnitude better than satellite, because satellite probably can push to megahertz or even a bit more. But one of the challenges is if it's a low Earth orbital satellite, you probably only have a set of view for about a few minutes before it's gone. So you do need extra memory, so maybe you need many satellites to kind of maintain such a communication channel. And if it's a high orbital satellite, you probably the collection efficiency is also something that one need to work on. But here, the VBG, it guarantees will have a high bandwidth, and moreover, it doesn't depend on weather. It can work all the time.
And final question is that is there any experimental proof of concept of this, or is just a theoretical analysis?
Yeah. So currently, I would say one strong indication it's possible is this gravitational wave detection that shows that actually, in principle, the photon can propagate over thousands of kilometers on the ground. And we are also collaborating with the researchers from Caltech, try to do some demo on this. And also, actually, another part which is interesting of the history of science is actually in the late 60s, people were also exploring using these beam guides for communication. And people even at that time, they just had that kind of laser technology and also demonstrate that you actually can get photons through. The caveat is at that time, fiber technology took over, because for classical communication, fiber is sufficient. However, for our quantum communication, we do need a large attenuation length. That is why I think it's actually an exciting time to explore this a vacuum beam guide technology for quantum communication.
Thank you very much, Liang. Thanks again for your presentation. And now we are moving to our next speaker. Our next speaker is Dr. Wolfgang Lüffler. He's from the Linden University, and he is a director of the Education and Institute of the Physics there. And his research is basically focused on using the quantum, high-dimensional quantum information. He was for a while a world record holder on the experimental high-dimensional quantum information, in fact. And then he also is leading the section on quantum matter optics on Linden. Since 2025, he is a holder full professor position. With that, I leave to Wolfgang to start his presentation.
Many thanks. Thank you very much also for having me here. I am Wolfgang from Leiden University, and it's my pleasure to tell you something about quantum position verification using single photons. Yesterday was the focus a lot on fully entangled quantum networks, and this is an application that is much simpler. It is more in the field of device-independent quantum networks and send and forget protocols. It's a collaboration of Leiden, in particular of Kirsten Kanneworf's PhD project, and the University of Amsterdam and QSoft with the group of Harry Burman, who is nowadays at Quantinuum. In particular, I will show you an experimentalist view on a number of problems connected to quantum position verification. Oops. So what is position verification? We want to authenticate a party without the need that the people who want to verify the authenticity of the party have to meet that party. For instance, as shown on the top right, if we assume that we have in Leiden in the top left of the map and Amsterdam in the top right, two verifiers, as we call them, and we want to verify the location of a third party, which we call the prover. And the idea is that the location of a party can be a very strong credential if it's a secured area or a building, or just a particular location in a data center. And the idea is now that the two verifiers, which trust each other and share a secret private channel, that they send information to the prover, who has to do a cryptographic task and possibly a quantum task. And then we repeat this, and then the prover returns the outcome of this task back to the verifiers. And if this communication, as Ramanya said, is done with the speed of light, this time delay is really limited by very holy fundamental physical principles. By checking the timing and the answers of the prover can verify their location. Now here I show also a space-time diagram, but in contrast to Ramana's, the time axis is going upwards. That is what experimentalists are doing. And on the horizontal axis, we show the position. In the middle, the prover who want to prove their location, and at the edges, the two verifiers. They send the signals. The prover does now, in the classical case, for instance, the XOR operation on the two bit strings X and Y sent by the verifiers. Now, in this classical example, unfortunately, this is never secure, because two adversaries that are positioned outside of the location of the prover of this certified region in space, they can intercept and copy the classical information as indicated here in this space-time diagram. And then at a later time, which is here at 1000 nanoseconds in this example, have both the information from both verifiers and can perform twice the classical operation, return the correct results, and everything within the time limit that the verifiers expect to receive an answer. Of course, quantum to the rescue. The no cloning theorem, you might suggest that this solves the problem, because then the adversaries cannot copy the quantum information. It turns out to be much more complicated, and that is where this collaboration between Leiden and Amsterdam actually started. So here I want to show now what we need to do with quantum information. The two verifiers send 2 photons to the location of the prover. The prover has simply a beam splitter and performs the so-called swap test, or in quantum optics called the Hong-U-Mandel experiment, which is an experiment that tests for equality of 2 qubits without being restricted to a certain basis. And I briefly want to indicate here, because I'm an experimentalist, so we can simply decompose the input state of the 2 verifiers by using creation operators, acting on the vacuum modes 0 and 0. Then we apply the beam splitter transformation, that is where the reflected photon picks up a phase indicated by the imaginary unit I here. We multiply it out and we see that the middle terms cancel each other. That means we get 2 photons exiting either in port 3 or port 4, but never into different ports. And that is an indication that the 2 photons have been equal, because if we give one of the photons, for instance here, a purple color, then we see that the 2 middle terms in the bottom line of the equation do not cancel anymore. And we get also the case that the photons are sent to the 2 verifiers. And this is a very important operation, and that actually connects to the issues connected to quantum position verification. This table shows that this is really much newer than any other quantum protocol, probably. In around 2000s, Adrian Kent came up with the first ideas and actually a patent about that. And then it took some time until actually Charles Lim in 2016 and our friends in Amsterdam in 2021, we developed them protocols that are loss tolerant. As Liang just explained, that is really a major issue with many quantum protocols, but it's much worse for quantum position verification because it can enable attack strategies that we need to avoid. The other column on the right shows slow quantum information, also connected actually to Liang's presentation before, because we rely on the speed of light limit. And so either we can buy very expensive fibers that just in the past years became commercially available with 98% of the speed of light, hollow core fibers, or we use free space. That's really problematic. And as many of you know, some people don't like that in networking. Or we use advanced protocols, as shown here on the bottom line, where I won't talk today. We are working on these protocols nowadays. I want to briefly show our demo experiment that we have been doing in Leiden. We make true single photons by using a 2-level system, indicated here by the 2 energy levels. We excite it with a laser. It is excited, and then the excitation can relax and sending out a true single photon. That is kind of different to the down conversion experiments and other nonlinear optical methods of producing quantum light, because here we have a true single photon nonlinearity. We have just to block the laser and then are left with a single photon. And this we do by using polarization filtering in our case. Briefly about our system, in the past decade, it has been worked out that the most ideal quantum light source probably turns out to be indium gallium arsenide quantum dot-based quantum light sources. They are also nowadays explored towards sources for photonic quantum computation, and we embed them in an optical microcavity in order to realize an efficient interaction. This requires long-term device design, which we did with friends in Santa Barbara, actually. And this shows a little bit the complexity of this design. But by doing this, then we have really a monolithic device which we can operate in a closed cycle cryostat relatively easily. Now, thanks to the optical cavity, we get a large amount of single photons, and this should just indicate that. So this shows a reflection and transmission spectrum of our microcavity without a quantum dot. And by introducing the quantum dot, we restore the reflection fully. And this means millions and billions of single photons are produced per second in this system, because these photons which are missing on the left are single photons. This shows now a sketch of our quantum position verification demo experiment. On the left is a part which produces the single photons in our cryostat source and contains also the newly developed technology for producing around 10 to 20 picosecond long laser pulses in a flexible way from a tunable laser. We then use a fiber switch to direct photons either to the two verifiers, because in our demo experiment we did not want to use two separate quantum dot sources, which has an extreme complexity. We synchronize the single photons by using fiber delays, in our case 200 meters of fiber. We encode the qubits of the verifiers by using polarization modulators indicated here by PM0 and PM1. We emulate the distance between the verifier and the prover by using also simply fibers on a spool. And then the green box shows the prover setup, which consists of 3 beam splitters. And that is what we also heard yesterday a couple of times. That is basically a partial Bell state measurement, what is here done, because at the first beam splitter, this Hong-Mandel effect that I tried to explain in the beginning is happening. And then the 2 other beam splitters are used to discriminate 2 photon detection events from potential loss in the system. And this kind of graph shows then our photon indistinguishability. And this is quite a hard task. It took us a decade also to develop this to this level, because we need to have photons that are produced at 1 microsecond apart with completely equal properties. And this is hard. There's all kinds of vibrations going on in the lattice. And this experiment shows that the photon indistinguishability is not bad, but also not perfect. The experiment is shown here in this photograph. And so we have a relatively small demo experiment using fully in-fiber components of most of the parts of the setup, with fiber switch also integrated and polarization modulators equally. By careful calibration, and this allows us to develop a model with which then we can compare our experimental results. Quickly to these results. On the bottom, we see on the left the raw measured coincidence events of 2 different detectors shown in the top, so AB, CD, AC, and so on. And on the right, we normalized these to detector efficiencies and related things. And without going now into detail, for orthogonal cent qubits, we more or less detect what we would expect, that is basically equal distribution of the photons. And now the blue bars indicate the events for parallel qubits, and then the two left dark bars are exactly what we would expect. However, in our demo experiment, we also have some unexpected coincidences, which we find is due to our insufficient purity of the single photon source. Anyway, I briefly want to mention what is the limit to demonstrate that quantum position verification requires quite stringent limits on the experimental inaccuracies. Because first, for the ideal case, if we have orthogonal qubits, as I mentioned before, the red bars, we have of these results, there is only two of three or four of six are actually the prover can return the correct answer, because the other ones appear like photon bunching, like the Hongo-Mandel effect. So 2/3 is correct. If we now send from the verifiers 50% orthogonal and 50% parallel qubits, then we get therefore 1/2 times 2/3 probability to have the right answer, and 1/2, the other 50% times 1, because in the ideal case, we would expect that we always return the correct answer, which is 5/6 of correct answers. And so we have to ask, what is the lower limit? And that is where the collaboration with Amsterdam, with computer scientists, comes into play, because to do this right, I'm going to now simply show the full, the full animation. This needs to be done by proper proofs. And basically, an attacker, what can they do? They guess a basis, measure the qubit in it, and then do their best to return the correct result. We have 3 bases for qubits. So the first possibility is they've chosen the right one in which the data was sent. And for the other 2 cases, there is a 50% chance that they return the correct result. So this is 2/3. And that means the margin for sending the correct result is rather small. And with this, I want to go to the end. And I hope I could show you that there is a potentially quite novel protocol suitable for quantum networks, quantum position verification, that might actually have real-world use cases. We are currently exploring this with many partners, and we have a first demo experiment which needs improvement, but we're working hard on that. And with this, thank you very much for your attention.
Thank you, Wolfgang. That was a very good presentation. In the interest of time, I have only one question to ask you, and then I know you're going to be in panel. You can ask the rest of the questions in the panel. What is in your setup, experimental setup and concept? The question from audience is that what is the difference between the device-independent QKD and QPV? Seems very similar.
Excellent question. This is also the basis of the Charles Lim paper from 2016, who realized that actually this setup is very similar. However, it requires speed of light communications. And currently, as far as I know, most device-independent setups, QKD implementations are done in optical fiber cable with 2/3 of the speed of light. And therefore, we have to use advanced protocols that combine speed of light radio communications with slower quantum communication. I'm happy to discuss that later in more depth.
Thank you. Thank you very much, Wolfgang. And now we are moving to our next speaker. Our next speaker is Mohammad Al-Getra. He's from KTH Royal Institute of Technology in Sweden. He's a researcher there, and his research is focused on single photon source quantum memories and their application in advancing quantum communication. With that introduction, I will pass the floor to Mohammad.
Thank you, Reza, for the invite and for the kind introduction. So I will be talking about a recent work where we have done this intangible purified time distribution across a network here in Stockholm. So this work is a collaboration between our group in KTH, the Quantum Nanophotonics Group, which is led by Professor Val Zweller, and Ericsson in Kista here. So just before I start, the outline of my talk will be a brief motivation about the need for synchronization or time distribution in quantum networks and in classical networks, really. Then I will be describing the source that we have used for this demonstration, which is quantum dots, similar to the ones that were used in the previous demonstration. And then I will talk about the actual intangible distribution of our work, and then move to the protocol where we have done the time distribution verified by entanglement measurements. So as a motivation, in the context of quantum communication, when you use photons for this in QKD, then you identify these photons by the arrival time, or by the generation and the arrival times of these photons with respect to some reference time frame or a clock. So in order to have a successful key exchange, for example, if you are using entangled pairs, then the ability to identify the one of the photons in one of the nodes and the correct corresponding photons in the other node, this is crucial in order to generate a successfully a key. And that requires a very high accuracy detection of or knowledge of the time of arrivals of these photons. So you need to be able to have a common time of reference or reference or clock between the two nodes, which can be challenging if you are using fibers for the communication, since these are affected by environmental changes, which then could create some drift with respect to between the two clocks, which directly translates into error in your generated keys, or a failure of the whole process, even if that's large enough. Similarly, another aspect of this, if we are talking about classical GPS-based synchronization, that is vulnerable to spoofing attacks. And then if we are talking about the entanglement or quantum-based synchronization, it gives a solution or a proof against such attacks if you are using some quantum properties like entanglement to verify the source of the synchronization signal. Okay, so moving on to the characterization of our source. So we have used quantum dots also, telecom-based quantum dots. In our case, they are not based, or they are not hosted in any cavities, so they are not as bright. But it's in the arsenide, in gallium arsenide matrix, and we use a DBR layer beneath the quantum dots to enhance the extraction. So the emission rate is in the orders of tens of thousands of counts per second of the entangled pairs. Now, one thing to know about these dots is that they emit the entangled state shown here, which is a time-evolved Bell state, and the phase that you see here is due to the fine structure splitting of the quantum dots, which originates because of the asymmetry in the confinement potential. So this is not a problem because it doesn't deteriorate the state, the quality of the entangled state. It is just a time-evolved entangled state. And there are methods of mitigating this phase, whether you are by erasing it using strain tuning, or erasing it post-emission using some wave plates and so on. So we have, before doing the actual demonstration, we have done local characterization of the generated entangled states. So we did the projections of 16 different bases, and in A here, in figure A, you see an example of 2 projections. Then from the raw data, we can reconstruct the density matrix at different delays. So the oscillation that you see here in the projections and also in the fidelity to the phi plus state is due to this phase that I mentioned, the time evolution. And we achieve a maximum fidelity to the phi plus of about 90% and about 89 concurrence. So we take this state. This is how the whole setup looks like. We take the state, so we generate it using exciting with a pulsed laser, picosecond pulse laser. The quantum dot is hosted in a cryostat. You extract the cascade, which is composed of the exciton and pi exciton photons. And these, in our case, both in the telecom C band, separated by about 5 nanometers, which can be separated using, for example, in our case here, a transmission grating. Then you can redirect each of them. In our case, the pi exciton was detected locally after sending it through this polarization projection optics, and then detecting it with a superconducting single photon detectors, and then using a time to digital converter to record the time tags. The exciton is then extracted and sent through a circulator across a fiber, 20 kilometer long fiber, to Schista, to a remote lab in Ericsson headquarters. And at the other end of the fiber, we have a partial reflector, an inline partial reflector, which transmits 30% of the exciton, which is then also sent after filtering into the polarization projection optics, then to detection and time tagging. And the 70% that is reflected, I will say why we reflect that in a minute, is redirected across the circulator and then detected locally at the master location here in our lab. Another important aspect of this is that the clocks or the time taggers in the two locations are externally clocked with a common reference. In this case, a rubidium clock at 10 megahertz, which makes sure that the frequency of the internal clocks are synced between the two time taggers. Okay, then first we do a remote quantum state tomography between the two locations, doing also 16 projections. And again, you see here the projections of the HV. And from that, we reconstruct the density matrix and we measure a maximum fidelity of 82% and a concurrence of 66%. Of course, in order to have this working, the fiber that we used for the communication is polarization stabilized. So that was not shown in the figure, in the setup figure that they've shown, but we have polarization stabilization across the fiber. Okay, so now we verify that we have the remote entanglement shared between the two locations. Then we can use the two correlation, or we can do two correlation measurements using the different detections. So if you remember from the setup that I have shown, we have detected the pi exciton locally, and then we have detected the exciton partially remotely and partially back also locally here. So we do two correlations, first between the locally detected pi exciton and the remotely detected exciton. And this will give us information. So this is what you see here in the blue curve here. It will give us the offset between the two clocks. Then, and in this case, it's shown here. So it's subtracted from the x-axis here. And then we do a second correlation measurement between the locally detected pi exciton and the returned exciton that is also detected locally. And this will give us the information about the round trip time. And by having these two informations, we can basically, and having the two clocks of the time taggers locked, then we can have absolute time distribution, basically, or for synchronization between the two clocks. In order to verify the authenticity of this, we added time delays that are measured separately using time of flight of 4.48 nanoseconds and 0.3 nanoseconds. And if this works, we should be able to resolve that as a shift on the correlation peak. So, and that's what we see here. So in the correlation measurement between the KTH and Chista direct detection, we see a shift of 4.54 nanoseconds. And between the local detection in KTH and the return detection also in KTH, that gives the round trip time, we see twice that shift, which verifies the method. Similarly, we do the same thing with the 0.3 nanosecond, and we also get similar results. So then this gives us an estimation of the accuracy of our method to be about tens of picoseconds. So yeah, before I finish, I should thank the people who contributed to this work, our colleagues here in KTH and our collaborators at Ericsson. And thank you for listening. I'm open for questions if there's any.
Hi, Mohammed. Thank you so much for your presentation. That was a great presentation. I have a couple of questions to ask here from audience. If you want to compare this to White Rabbit protocol, what would be advantage here?
That's a good question. So the first aspect is that this is verified by entanglement. So it is secure by the entanglement measurement, basically. It is secured against spoofing attack, thanks to the no cloning theorem that has been discussed earlier. So that's one aspect of it. And I believe that the tens of picoseconds, and here we are limited by the brightness of our quantum dot. If we have to acquire for many hours in order to get any of these correlation measurements. If we have a brighter source, then I believe we can achieve even picosecond level of synchronization, which I believe is far from what the White Rabbit can do. I think it's hundreds of picoseconds, or on that level.
Okay.
So yeah, that's the advantages.
And a final question from audience is this need to be a point-to-point or can work in a network that you reconfigure? Is basically the length changes continuously?
In principle, there is no limitation. It's not point-to-point. It can be used in a starfish sort of topology. The limitation, though, here, I should say that the brightness of the source is limited, even if we embed it in a cavity, and then quickly you will have to limit some scaling. Your scaling will be limited, is what I'm trying to say. So the signal will be weaker the more you distribute across different parties, and then at some point, it will not be scalable enough. So then I would say a demonstration across a few parties is possible, but you cannot scale it to tens of nodes, let's say.
Okay, thank you very much for your presentation again. Now we are moving to our next speaker. Our next speaker is Professor Alessandro Federici. He is a professor of quantum technology in Heriot-Watt University in UK. And he currently holds an early career quantum technology fellowship from EPSRC, a UK Research Funding Council. And he also has had an ERC Discovery Early Career Award and has been a research fellow of Andrew White at the University of Queensland in Australia prior to Heriot-Watt University. With that introduction, Alessandro, thank you for joining us, and the floor is yours for presentation.
Hello, yes, thank you. Thank you, Reza, for inviting me to the summit. So what I would like to talk about is multi-user quantum networking applications. But before I come to that, I'll talk a little bit about the current state of the art of quantum networks, how we will progress from trusted node networks to untrusted networks, and what we're doing about this currently in the UK. So the starting point, of course, is QKD for cybersecurity. Why do we need that? Because quantum computers are now getting to a stage where perhaps within a decade they will start to threaten the security of the RSA public key crypto system. Now we have post-quantum crypto, and that's already being rolled out. However, this perhaps could be only a stopgap because it's not proven yet that that might not be vulnerable to a quantum computer. So a secure way of getting a key between people is quantum cryptography, where you establish randomness without that being hackable effectively. So in the current commercial version, the way this works is you send single photons or attenuated lasers from Alice to Bob. You encode some random states, you do a bunch of measurements, you reconcile the measurements with what was sent, and that gives you a classic key, a classical key that you can use for encryption. Now, the way we turn this into a network at present is we have these point-to-point connections here from A to B, from C to D, and these individual connections are limited to the distance of a few hundred kilometers at most because of the loss in the fiber. And so if you want to get a key from A to D over a very long distance, the way this currently works in trusted node networks is you do an XOR operation at this B and C node. What that means is that the node has to be trusted, the node knows the key. So that is the state of the art of current network demonstrations. This works over long distances, but is somewhat undesirable unless you do own the nodes, I suppose. So in the UK, we do have a network like that. So that is in the south of England. It stretches from one side, Cambridge, BT's headquarters at Adderstral Park, through London, and then to our chair's former stomping ground in Bristol. The commercial backbone of this network is mostly provided by Toshiba UK, and you can now buy their boxes of them also commercially. A recent demonstration, this was a fully software-defined network with key management and all the rest of it, as you would expect it in a classical network, but it had an underlying quantum key distribution as its basis, and that achieved sort of a 410-kilometer dark fiber connection all the way from Cambridge to Bristol. Right, that is a very small network compared to what the biggest network currently looks like. So this is the Chinese quantum network published earlier this year. They now do carrier-grade quantum comms over 10,000 kilometers, where there's lots of metropolitan networks involved, and also satellites for genuine long-distance connections. But again, all these nodes in the middle have to be trusted, so they all theoretically have access to the key. Now, you can, what can you do in order to move from trusted nodes to untrusted nodes? You can use entanglement. So here, instead of sending stuff from Alice to Bob, you have a source in the middle. It sends entangled photons to both of your parties. And these entangled photons now have these correlations, which are stronger than classical. And what they do is when you do a measurement of, say, a spin or a photon polarization, it will always give you a random outcome, but it will be the same outcome for both parties, and so they can establish random keys. Now, how does that now help you to extend distances? Well, you can now have entanglement between A, B, and C, D instead of just laser pulses. And then in the middle between B and C, you can do these so-called Bell state measurements. And what that allows you to do is it allows you to extend the entanglement link directly from A to D. Now you can do this in a linear chain and do this many times. And so you can extend the distance further and further. However, if you just wait for photons to arrive at random to do your Bell state measurements, what you get is still an exponential loss drop-off. And to avoid that now, you can put quantum memories at these sites. You can store a signal that comes in from one link, and then you can wait for a signal to arrive from the other side. And that by synchronizing these two signals, releasing them from the memory when you need them, you can then turn this exponential loss behavior into a linear behavior. And this is currently how we're thinking that large-scale entanglement networks will be created. Now, the ultimate vision, of course, and this is also the basis of many papers that study quantum networks and how to distribute entanglement in quantum networks, is that you have these, dozens of nodes, maybe hundreds of them, and that supposedly there is entanglement between all of these endpoints. And what that means is that you have multipartite entanglement, so something like a GHZ state that connects maybe people in different capital cities across Europe. There is, however, a big question of do we actually need this? Because quantum cryptography ultimately is between two parties, or at least that's how it used to be. There might not be a need for multiple nodes to be entangled. Maybe all you need is to be able to share some pairs or some correlations between two nodes. What I'm trying to convince you of is that there is, in fact, a use case for a multipartite entanglement. But before we get to that, what are the potholes on the way to turning from these trusted nodes networks to untrusted node networks based on entanglement? Well, there's lots of potholes, just like in the UK. So there's the quantum memories are still very immature, so they're not ready yet. They don't do what we need them to do. The infrastructure isn't there, so we have to rely mostly on dark fiber, at least for the backbone. We need more satellites for truly long distance and intercontinental connections. We need research access to this infrastructure, which is not always guaranteed. And a lot of work needs to be done on regulation, standardization, and assurance. So all of these things need to click into place before we can have truly global quantum networks. So in the UK, we're trying to drive this progress through the Integrated Quantum Networks Hub. So this is a hub has been in place now for a year, following on from the Quantum Communications Hub that we've had for the last 10 years. This hub is now led by Heriot-Watt University, so that's my institution, in partnership with 12 other universities and 2 national labs. We have 40 industry partners, and the goal that we have for the next 5 and then hopefully 10 years is to ultimately deploy a UK-wide quantum network that is based on entanglement. Right, so what is my lab contributing to all this? Well, we specialize in quantum light source development, and primarily I'm interested in generating very high quality telecom light entangled from optical processes, in our case, nonlinear crystals. We have quantum dots, however, as well, and I believe we are the current long-distance record holders for QKD with telecom converted quantum dots. We can do this over 250 kilometers with decoyed state protocols. We're also working on satellite QKD, so we have our own ground station at Heriot-Watt campus, and we're eagerly awaiting the SPOX launch. That's a UK satellite, but we're also contributing to the Canadian KeySat mission. And the topic of this talk today is however, quantum networking with multi-party entanglement. So how does that work then? Well, we make entangled photon pairs in nonlinear crystals, and what we've pioneered over the last 10 years or so is that we can make very high quality pairs by domain engineering these crystals to impose very specific spectral shapes to our photons. And what that does then is it gives us very high brightness photon pairs, very high quality entanglement. We don't need any filtering, which means that we have a very high efficiency of getting these photons into fiber. It's all a telecom, and we can then fuse these photon pairs into so-called network entanglement. So we can turn individual bell pairs into so-called graph states, which can then have an entanglement connectivity, which mimics that of admittedly small-scale networks. Now, this doesn't work at very high rates. We rely on probabilistic effects. However, as you may know, there are companies now who are trying to build quantum computers based on exactly this sort of thing. They have much more funding than I do. So it's quite realistic to expect that this will soon be doable also deterministically. So what are now these applications that I've been promising? Well, since 1984, QKD effectively has been limited to just Alice and Bob. So how do you get a key to these 2 people? But just like in the summit today, the situation we sort of more often find ourselves in now is, of course, that we're communicating to multiple people at the same time. It would be nice if you could generate a secure secret key between all these users at once without having to establish, individual pairs with each single Bob here in this communication link, because that's going to clog your network. Now, it turns out there is a protocol for that. Now, in conventional Alice to Bob entanglement QKD, you use these correlated photons. You send one to Alice, you send one to Bob, and they end up being correlated. But it turns out you can use multi-party entanglement in the form of a so-called GHZ state, where you have not 2 photons, but maybe 3 or 4 or 5 or 6 or more that all share this correlation. So whenever one user measures vertical, all other users, all end users will measure that same polarization. So it's been shown that you can use that to directly extract a secret key bit between end users. And this is exactly the sort of thing that we've been doing for the last few years. So in 2021, we demonstrated that we can send 4 entangled photons in a GHZ state over up to 50 kilometers to extract key for conference purposes. We've shown that that works in a network. So here we had 6 users where 2 were eliminated. So this is the kind of thing you'd have in a fully connected network. Sometimes you have to eliminate a node before you can have the other ones connected. And so what we can show there is that you do have a genuine efficiency advantage where you need to use the network less often than if you had to rely on pairwise connectivity. And we can also do this for anonymous conference key generation. So here the goal is that some of the users in the network aren't aware of who else is doing a conference key in a certain session. And in this case, you can get a quadratic speed up on the amount of network use, which in our case was almost 150-fold and 150-fold advantage. So just to be clear, the advantage here is not in the direct transmission. That would be hopeless. If you want to transmit, say, 10 photons at the same time over any sort of distance, then you have a really bad loss scaling. The assumption here is that these multipartite entangled states are provided by the backbone, by the network, already error corrected and all that, and that you simply use this network, and then this is the more efficient way of doing it. So this was the conference key stuff, but we've also had other work on network non-locality, for example, on quantum communication complexity with multipartite states, and also most recently quantum private distributed sensing and quantum secret sharing. So I'll show you a slide each on these 2 applications, and then I'm going to close. So quantum secret sharing is related to conference key agreement, but it's not the same. So the goal in secret sharing is that a sender shares a secret with n-1 receivers, and the receivers then, if they want to use the secret for something, they have to come together and cooperate. Otherwise, the secret will be useless to them. So this can be used, for example, in e-voting. Now, in conference key agreement, we use GHZ states, and then we do Z measurements for the key and X measurements to check whether it's working. In the secret sharing scenario, you reverse these 2 measurements, and effectively you do X measurement for your key bits, and then Alice can do Z measurements to establish effectively which parity she's sharing with the various Bobs. Now, secret sharing is an old protocol. This was around already in the late 90s. But it turns out that was never fully secure. It was always prone to an attack, and it also wasn't composable in the modern sense for the security proof, and also didn't have a finite key rate analysis. So this all was recently addressed by our collaborators at the Freie University in Berlin, Jens Eisert's group. And together with Jens Eisert's group here, with Nathan Walk and Janka Memmen, we've just done an experiment on this where we got up almost 250 secure bits per second shared between 4 people, all separated by 5 kilometers of fiber, again using GHZ states. Final application, distributed sensing. So this is something that now is always brought up as another application for quantum networks. It turns out, however, that there aren't that many protocols which actually gain an advantage from being in a network. We believe that this is one of the first examples of such an advantage. It doesn't come in the measurement, though. It comes from having quantum privacy when doing a sensing task. So the goal in this task that we looked at was to estimate a global function, the sum of local parameters theta, without revealing the thetas to anyone else. There's 2 steps involved here. So first, you need to verify that the state is a proper GHZ state, and that consumes a lot of rounds. And then you do the estimation. So you do measurements with your photons, directly estimating phases of, say, a wave plate angle. And then you do a whole bunch of analysis that I'm not going to bore you with the experiment again was entangled photon sources fused into a graph state, into GZ states. Now, what we saw there was that we can indeed estimate local phases without revealing them to anyone, and we can do an estimate of the global function, which you can sort of show by Fisher information arguments that no information is leaked and so on and so forth. Now, this protocol wasn't amazingly efficient. It has lots of caveats. But again, just like these other applications, it's one of the first of its kind demonstration that there is something that you can do in a network which does gain an advantage from having multipartite entanglement available. And we hope that this sort of thing inspires many more experiments and applications to truly justify a business case for a fully connected quantum network. And with that, I'd like to close, and thanks for being here.
Thank you, Alessandro, for a great presentation. We have a couple of questions. Let me bring the questions that I ask you. One question is that what would be the advantage of having multipartite, multi-user quantum network compared to the multi-point-to-point bipartite connectivity in the network?
Yes, so the advantage in that we have demonstrated is that you need to use the network less if you have the multipartite entanglement, if you're interested in having multiple people cooperate. So this could be for conference key, but it could also be for secret sharing or sensing, or in fact distributed computing, right? By providing multipartite entanglement, you can work directly with a single network use between multiple people, whereas if you had to break this multipart, or if you had to do pairwise connections, then you need to wait till all these pairwise connections have been established, and then you need to algorithmically make sure that these people now share a common key or whatever you want to do. Now, for distributed quantum computing, of course, you will need the coherence in the first place, so that generally probably cannot be done with pairwise connections.
Thank you. And the final question is that you mentioned that one of the problems is that the source generating graph state is probabilistic. And what are the possible way to make it deterministic? I mean, can you comment on that?
Yes, absolutely. So first, I would like to say that sometimes there's this divide where people say quantum dots are deterministic and optical sources are probabilistic. That is not really true, because quantum dots also have loss, and as soon as you have loss, things are probabilistic, right? I think both architectures have a way to get to determinism, but it will most likely in both cases have to involve a certain amount of multiplexing. So if you look at how certain quantum computing companies are tackling this issue, is instead of just having a single photon source to make a single photon pair, they have maybe 10 or 50 or 100 photon sources that make 100 photon pairs. And then you look at one of these photons and wait till one of them actually fires. And if one of them fires, okay, there must be a second one somewhere. And then you use a very low loss switch yard to switch it all into a final signal line. Now, obviously, all of that also has loss, but then you can show that if you can reach certain thresholds, then you can deterministically, or at least fit for the purpose, make multipartite states.
Thank you, Alessandro. Thanks again for your talk. Now we are moving to our next speakers. So our next speaker is a team from Cisco. We start with a presentation from Andy Kaur, which is our technical lead for in quantum research team for software and theory, and then we continue with Suresh Kasiri, which is from the engineering team. So I leave the floor to Cisco team to start their presentation and demo.
Okay, can you hear me?
Yes.
Okay. So thanks for joining, everyone. I'm Anit Kaur. I'm a researcher at Cisco Quantum, and I will be talking about quantum network empowering classical applications. So broadly, we can classify the applications of quantum networking into two categories. The first one is quantum for quantum. So we want to link quantum computers together. Think of multiple QPUs in a data center and connected together. So we use short distance entanglement networks and a compiler layer to coordinate them. And this is what we talked about in yesterday's presentation. So have a look at it. The topic of today is quantum for classical. And basically, we're using entanglement to make today's networks better. We're talking eavesdropper proof security, quantum telepathy, time sync, and position verification. Some of these topics we have just discussed in the previous presentations. But the clue between all of these, quantum for quantum and quantum for classical, is a quantum network distributing high fidelity entanglement. So at Cisco, we have developed quantum networking components. So we have a telecom source. So this is a chip scale entangled photon source developed with UCSB. It's powered by a laser pump and it outputs entanglement in telecom wavelengths. This module is small, it's integrable, and it's stable. The next part that we have is a dual frequency source, which is developed in collaboration with Connect. It uses rubidium-based ensembles, producing one photon in the near infrared and the other one in telecom. Um, so basically, this produces one photon in infrared, which is compatible with quantum memories or QPU interfaces, and the other one it's in telecoms, useful for quantum networking. So this lets us bridge systems operating at different wavelengths. The next component that we have is a quantum switch. So it's a programmable device that routes entanglement between nodes while preserving their quantum coherence. Coming to the quantum network software stack. So at the top, you'll see two applications APIs. So we will be giving a demo on both of these applications. The first one is quantum eavesdropper proof security or quantum alert, and the other one is the quantum sync. Um, in the middle, we define a library of quantum network protocols. So basically, entanglement distribution protocols or swapping and teleportation. So these are all modular, they're composable, and they form the network logic layer that the compiler or the applications talk to. At the bottom layer, we interact directly with the quantum networking devices. So that's sources and switches and detectors. These can be real, emulated, or simulated depending on what application you're falling into. Okay, so the first application that we will talk about today is quantum sync. So let's look at the task at hand. So that is tacit coordination. So imagine that you have a user A and user B and sitting in labs 50 kilometers apart. So at time t naught, they each make observations. Now, to share these observations, they need to communicate. But light travels only so fast, and 50 kilometers can take about zero point 0.1 millisecond. Now, suppose that they need to make a joint decision at time t1. So faster than information can make that trip. So that means that neither party really gets to communicate the observations that they have had. And the best that they can do is go blind. So that's where quantum mechanics flips the script. So if two labs, they share entangled particles and they have their own observations and they measure these particles based on these observations, the outcomes are correlated and these correlations are stronger than what classical mechanics allows. So each side, it can perform a local measurement and without exchanging messages, they will end up with outcomes that are correlated. Um, these correlations are basically stronger than what you can get from classical correlations. So we call this as tacit coordinations. So just to recap, you're given a global function and this needs optimization. Communication is forbidden between user A and user B. The best classical strategy that you can do is have some previous agreed upon decisions. You can't dynamically change your outcomes here. So you see an observation and you take an action. Quantum strategy with entanglement shared it gives you a like you see an observation, then your measurements are going to be dependent on that observation, and then you can make a decision based on that outcome. So let's look at the CHSH game. So this connects nicely to the idea of quantum synchronization. So this referee, it sends random bits L and M to user A and user B. The two players, they must output answers that satisfy the winning condition that's there on the screen. The best classical strategy here is that you always output 0. For whatever be the L and M, just output 0 and you'll win 3 out of 4 rounds. So that's the winning probability of 75%. But if you use a quantum strategy, and if you share entanglement and you measure cleverly, you can boost this winning probability to 85%. And why does this matter? Because the winning condition essentially encodes a form of decision coordination. So Alice and Bob, they're trying to optimize a global function, which is given as the winning condition, and they cannot communicate. And quantum helps with winning it with a higher percentage. That's exactly the kind of primitive that shows up in real world scenarios like high frequency trading, where decisions need to be coordinated. Okay, so let's break down the quantum strategy for winning the CHSH game. So Alice and Bob, they start with an entangled pair. Let's assume these are polarization degree of freedom. Now, they each get one bit from the referee, so L and M. Based on them, they make some measurements, and the measurement angles are given on the screen. There's no classical communication, just local measurements, pre-agreed strategy, and entanglement doing its job. So with this setup, the answers satisfy the CHSH winning condition 85% of the time, which beats the classical cap of 75%. So that 10% bump, that's quantum-enabled coordination boost, and it can open door to real-world applications, including time syncing the decisions. Okay, so let's unpack this table, which basically shows what quantum, like how quantum helps. So look at the outcomes that are given over here. In classical strategy, you're going to win 3 rounds, but with the three of these rows, but deterministically. While in quantum, you're not going to win all of them deterministically, but you'll win all 4 of them with 85%. So that's how it adds up to 85% winning probability. Now, of course, it's not perfect. You're not going to win 100% of the time, but that's a limitation from classical as well as quantum, if no communication is allowed. So this is not perfect, but it's still an advantage, a quantum advantage. Okay, so going to the usefulness. So one place where decision coordination can be very useful is the high frequency trading. So the servers here are 56 kilometers apart, and it takes about 188 microseconds to make that trip. So, firms are already spending, to shave nanoseconds of their latency, and this can help. Quantum networks can give a new edge. So by pre-sharing, you can be allowed to synchronize decisions and hedge risk faster. Okay, so now I'll move to the quantum sync demo. It's a tool for people to build their own network for to test out the network that we have for decision coordinations or for any other applications. I'm sorry, give me a minute. Okay, so here is the demo that we have for quantum sync experiment. Okay, so the cornerstone of our quantum decision coordination is entanglement. And what we have here is a, just to make sure, you can see the demo screen, right?
Yes, that's correct. Go ahead.
Okay. So Okay, so the cornerstone of our of the experiment or of the quantum sink is actually an entanglement distribution. Now, for entanglement to be actually useful, we need to understand how good that entanglement is, and that's what we provide over here. It's a simulation tool to test out your entanglement. Okay, so we start with a Cisco entangled source. So let's look at the experiment setup here. We start with a Cisco entangled source. It has, so it generates entanglement and sends it to fiber to user A and user B through these fiber spools A and fiber spools B. Now, this user A and user B, they can perform measurements, and based on that measurements, they can make their decisions. So what we have in this experiment are two kinds of parameters. The first one is the controllable parameters. So these are parameters that you can tweak in your experiment, like the measurement basis that you end up selecting, or let's say the entanglement source that you have, or the distance that will impact the fibers, the fiber efficiencies. Um, the other set of parameters is these are like observed parameters. So these are set in your there. These are more tied up to what kind of experimental setup you have, but we still give them as tunable so that you can understand how your particular choices of measurement basis and source helps, and what kind of impact does noise have on your entanglement, and in that way what kind of impact does noise have on your applications as well. So let's start with the parameters now. um, we have the probability amplitudes. So these are the entanglement source parameters. So you have the probability amplitudes and the phase parameter. So this controls the kind of entanglement, like the type of entanglement you end up producing from this entanglement source. Next parameter here is the visibility. Ideally, you want this to be 1, but that's not always possible because of some noise that can be present in the experiment. Okay, so next we come to the link parameters. So once your entanglement source generates entanglement, one photon is going to go to the user A and the other to user B. And that's happening through these fiber spools A and B. So that we have two parameters for the link itself. The link efficiency and the depolarization. The link efficiency is just the fraction of photons that end up reaching user A or user B. So if it's 1, that means all photons are reaching. The next one is the depolarization of the fiber. So this is different to photons being lost. This is more about entanglement having noise in it or being corrupted, or the correlations in entanglement being corrupted. So these are two parameters for the fiber spools, and the link efficiency that's related to the distance you might have in the fiber. Coming to the measurement parameters, we have two um, uh, two observed and two controllable parameters. So by controllable, I mean you can basically choose your measurement basis. So you can choose your theta and you can choose your phi, and that defines what measurement you will be performing on user A or user B side. Then we have two other parameters, the noise parameters, and these are the detector efficiency. So basically, what fractions of photon which reach the detector are actually detected. And the second is the alignment factor. So how close is your measurement basis to the actual measurement basis that you want? Okay, so once you have all of these parameters specified, you have basically described the experiment, or all the noise sources and all the tunable parameters in the experiment. Okay, so once you have that, you can click on the calculate probabilities and you get certain metrics. So the first one is the heralding efficiency. So this basically means how many of the photons that were generated, or the fraction of photons that were generated and they reached Allison bomb, or the user A and B. So if this is 1, basically means all. As it goes lower, you'll have low fraction, less number of photons that's going to reach user A and B. Okay, so coming to the tomography part, So the tomography is basically a representation of the density matrix of your entanglement that ended up reaching Alice and Bob. It has two parts, the real part and the imaginary part. And what you see on the screen right now is for a perfectly entangled state or the ideal state that you want. Now, the density matrix, which is represented here in the graphs in terms of tomography, it has all the necessary information that you would want. So based on that, you can calculate any metric or any kind of, application, how that entanglement is useful for that application. So you can calculate or you can simulate any type of the impact of noise on your applications. So we have given this, and you can play around with this part. Coming to the third metric that we give, that is the measurement outcome probabilities. So basically, whenever you choose your measurement basis, you're going to have um, measurement outcome 0 or 1. So this implies Alice has a 0, Bob has a 0, Alice has a 0, Bob has a 1, and so on and so forth. The photon lost is basically related to the heralding efficiency. And on the y-axis, you see the probability. Now, right now, what you see here is a perfectly correlated distribution. So whenever Alice gets a 0, Bob gets a 0, Alice gets a 1, Bob gets a 1. This is the ideal distribution that you would want. Going on, if I introduce noise in the system, so let's make the depolarizing noise higher. You can do your calculate probabilities again, and what you see is that the tomography, it basically changes. So this is no longer a maximally entangled state. There has been a loss of correlations. And if you come to the measurement outcome probabilities, again, you see that the distribution has changed. You also have 0, 1, and 1, 0. And this kind of goes back to the point that the depolarizing noise impacts the correlations that are present in your entanglement. Okay, so now this, let's just change back the depolarizing noise to 0, but introduce some kind of a measurement basis change. Now, if you change the measurement basis, it doesn't really impact all the tomography because the state itself hasn't really changed, but it will change the measurement outcome. So you see that you're no longer sampling from perfectly correlated distribution, but actually a random one. And that's because the bases themselves are not aligned, and that can also lead to, that will lead to this kind of a random sampling for measurement outcomes. Okay, fine. So now based on all these parameters, we have what the entanglement will look like. You can simulate it. You can see how measurement impacts, like how the entanglement and measurement basis impact your correlations. But, and you can use this for studying any kind of, or simulating any kind of applications you might have. Now, coming to the quantum sync game, this is the CHSH game, and I talked about it in the slides. For this one, what we want to see is how is the noise impacting your winning probabilities. And you can adjust your noise and your entanglement source parameters. So these are all adjustable. You can adjust your link parameters and the measurement parameters as well. And you can do calculate the probabilities for CHSH game. So what you will see is what is the winning probability here. So right now, because everything is ideal, you win the CHSH game by 85%. So by winning, we actually just talk about, you had a global utility function or the winning function. So if you play this game, referee gives 0, 1, and 1, 0 inputs. Given these conditions, given the aligned measurement basis, you will win this game 85% of the time. That's better than the classical threshold, which was 75%. But now, as we change the link efficiency, introduce noise in the system, we see that you're not going to win it as strongly. So now the winning has dropped to 76%. As you change or introduce more noise in the system, you'll see that your winning probability drops even further. So based on the noise in the system, based on the noise in the experimental level, you can see whether you're going to win the game, lose the game, and you can use this tool to study how noise impacts your other applications as well. Okay, so with this, I'd like to move to the second demo that we have. Let me share that. Okay, just to make sure, do you have the presentation now?
Yes, correct.
Okay. So the second demo that we have is different to what I talked about before. It's different to quantum sync, and we call it quantum alert. So what's that? So quantum technology isn't only for tomorrow's quantum network. It can safeguard today's classical links as well. So the use case I'll show, it's called Quantum Alert, and we will demo it live from our Santa Monica lab. So picture a simple task. You're sending valuable data from site A to site B. On today's infrastructure, someone can tap that line without leaving a trace. Our goal here isn't to encrypt that traffic, but it is to detect when the link is being tapped. So we set up Alice at A and Bob at B. Alongside the classical data, we use our telecom entanglement source to generate photons in the C band. So one photon, it stays secured at site A. Its partner travels to site B over the same kind of channels that basically same kind of classical channels. And we continuously monitor the coincident rate between them. So this is a metric that we use to kind of detect if there is an intruder or not. So now the quantum physics here does kind of the heavy lifting. Any disturbance or any intruder in the fiber ensures that any attempt to sample the quantum signal, it basically disrupts its correlations. So if the shared path is compromised, you see a drop in the non-classical correlations, and our coincidence watchdog basically raises an alert. Because everything runs in the C band, it fits in the standard DWDM channel and coexists with ordinary traffic. Um, we're not using this to share keys, but rather to detect the presence of an intruder. So this is the Cisco's tunable entanglement source. So basically, this is a reconfigurable entanglement source. On the chip here, you'll see several micro-ring resonators, each with different radii. So each ring has its own free spectral range, or FSR. It's basically the natural wavelength spacing of that ring. So whenever we inject the pump laser at the right wavelength, the ring generates a pair of telecom photons, which we call the signal and the idler. And what we do is we use on-chip control to fine-tune each ring resonator so it lines up with the exact C-band channels that we want to use. So in the example here, the R1 produces this S and I1 and so on and so forth. They're separated by 2 FSR. Okay, so the output from all of these micro ring resonators, they're combined, and from this tunable, they're combined on the chip. A tunable optical filter then selects whichever signal idler pair the network needs and sends them to two paths. Each path is detected, it is time stamped on separate time taggers, and based on this information, we can compute the coincidences for the quantum alert measurement. Okay, so this is an advanced version of quantum alert, preserving the high classical data rate without sacrificing the security. Basically, we add the major difference is that we add a quantum channel hopping, and that channel hopping is driven by a random number generator. So our source, it can create multiple signal idler photon in distinct ITU C band channels. So the RNG, um, randomly picks which channel to use at each moment. At site A, we split that pair. Um, we split the pair, and one photon is heralded and timestamped by the time tagger 1. its partner is wavelength multiplexed with the classical data and then send it over the classical channel and send it over the fiber. It goes to side B. So the controller here basically uses the same RNG output to select the channel matching and routes it to the quantum detector and the classical client. So because we were doing channel hopping using a random number generator, the eavesdropper doesn't really know where to look. So the best strategy is just a passive tapping attack. And this tapping attack is basically reduces the quantum correlation, and then that can be detected by the time tagger 1 and the time tagger 2, and it raises an alert. Okay, so here's the test bed that we will have for the quantum alert demo. This is not the more advanced version, but the simpler one that I showed in the previous slide. So we'll have two cases. The first with no eavesdropper on the link, and then with the eavesdropper present. So in this demo, there is no channel hopping. The ITU channels for both the quantum and the classical signals are fixed. Okay, so the entanglement source, it's tuned for high pair rate. We separate the pairs by wavelength. At user A, the signal photon is detected. It's time stamped by time tagger 1 to provide the herald. The idler photon is sent through the fiber spool and to the user B. At user B, the demux basically separates the quantum channel and the classical channel. The idler is detected and it has its time tagged by the time tagger 2, and then we compute the coincidences. The classical channel is received by the classical receiver where we observe the packet error rate. Um, Okay, so now this one which I showed is without the eavesdropper, and the case 2 is with the eavesdropper. So basically we introduce a passive tapping by the eavesdropper, and it's a 1% optical tap. Now this tapping is pretty weak. It's weak that the classical receiver will not actually notice it. So in the demo, the moment we introduce this tap, the coincidence rate between time tagger 1 and time tagger 2 drops noticeably. That reduction in quantum correlation triggers an alert and tells you, okay, this link is being tapped. So the POC testbed and is available on request. So you can submit your request through the Cisco Outshift website. And now I'll hand it over to Suresh, who will be demonstrating the quantum alert demo. Thank you.
Thank you, Vineet. Hello, everyone. My name is Suresh. I'm a software engineer here at Outshift by Cisco. Today, I'll demo Quantum Alert, one of our quantum applications for classical use cases. Let me share my screen. All right, so let me get into Quantum Alert. Okay, as Vineet explained, the main objective of this concept is to identify the eavesdropper in the channel while transmitting classical data using quantum techniques. This demonstration will run on a real hardware setup in our Cisco lab located in Santa Monica. Okay, let's take a look at the diagram. This is a block diagram, illustrates the experimental setup in our lab. Let's touch base on some of the major components. And for reference, we have attached pictures of each hardware device from our lab. Okay, here is the user A and user B. User A represents Alice and B represents Bob. And A sends classical data packets to user B. And so we have utilized a Cisco optical transceiver to send the data packets, and as well as other end, Bob receives from the classical receiver. These are very sensitive receivers. These can detect low power signals, but are unable to identify eavesdropper. The next component is Cisco entanglement source. So it generates entanglement pairs as signal and idler at different wavelengths. The source is optimized to identify the optimal resonance frequency, producing entanglement pairs at the desired ITU channel with the highest pair rate. The next device, the major component is quantum detector. The bottom portion, the cylindrical yeah, uh, device is our detector, and top one is the time tagger. Yeah, detector basically detects the quantum photons, and the top one is the time tagger. Detector sends a signal upon photon detection, then time tagger captures the time of photon detection on both user A and user B side. So as you notice, we have time tagger 1 located at user A location and time tagger 2 located at user B location. So yeah, as Init mentioned, we use coincidence measurement between time tagger 1 and time tagger 2. So coincidence measurement refers to the number of entangled pairs detected and measured simultaneously at detector 1 and 2. So this is one of the core measurement to identify the existence of an eavesdropper through the optical link. And also we have an emulator set up here to represent eavesdropper. This is optical coupler with 1% tapping. All these components are controlled by our quantum controller software sitting on top of this setup. It issues commands to each hardware agents and hardware devices and help orchestrating multiple steps to run this experiment job. Let's move on to the bottom portion. Here are a few configuration parameters that we can set up before running the job. Uh, so yeah, the first field is coincidence threshold. As we talked earlier, coincidence measurement, this coincidence range varies due to multiple factors and settings. So we optimize the source and other factors such as resonance, temperature, etc. to establish a perfect link for our baseline. So we need to capture the coincidence threshold value for a given time range with the baseline measurements. For example, if I choose coincidence threshold as 90%, that means anything falls below the 90% threshold, I want to get alerted. That means there is something going on in the channel. It indicates some issues such as an eavesdropper in the channel. The next parameter is number of failures. You can choose number of failures. Let's say we capture coincidence measurement every second. So, and this field determines how soon we need to get alerted and say how many points fall below the threshold line. And the last one is the time window. So it defines the time window to consider for capturing average coincidence rate and define the threshold value. Okay, all right. So before clicking on this job, starting the quantum alert demo, what happens when I click this button? So in the behind the scenes, our quantum, it submits a job request to our quantum controller, and controller starts issuing commands to our hardware devices. And one of the major, like, it has like four endpoints, like 4 components it will be communicating. Cisco entanglement source, it starts generating entanglement pairs. Then classical transmitter starts sending classical data packets, and other end, time tagger 1 and time tagger 2, they start collecting the photon detection timestamps. And also intermediately I will manually enable this eavesdropper. So we manually introduce eavesdropper in the channel and notice how the coincidence measurement impacts. All right. Also, as I mentioned, coincidence measurement is one of the measurement we track, and also in the classical data, packet error rate, also we capture and monitor. Okay, let's run the demo. So as I mentioned, yeah, I set 90% coincidence threshold based on my baseline metrics. It defined dynamically generated 5,300 pairs right now. So this is my baseline measurement, and the dotted line you can see it's my threshold percentage. And the below graph represents the classical data, the packet error rate between user A and user B. Right now, everything goes fine. There is no eavesdropper in the channel, and coincidence rate is pretty consistent given the classical data. Let's see for a few seconds, then I will start introducing our eavesdropper in the channel. It's a coupler with 1% tapping. So, okay, let me introduce eavesdropper. As you see, as soon as I introduce 1% tapping with our emulator setup, coincidence percentage started falling off, and I chose 10 points. If 10 points falls below the threshold, I need to get alerted. So as you see, I already got alerted. For demonstration purpose, I'm letting it run for a few more seconds, but in reality, this is where user A else needs to stop sending data and take precautious measurement what's going on in the channel. But it clearly indicates there is a eavesdropper in the channel. Okay, now let me remove the eavesdropper from the channel and see how this coincidence measurement impacts again. As you see, again, it goes back to my baseline measurements and goes consistently. And if you notice the classical error rate, there is no difference even with eavesdropper in the channel or without eavesdropper in the channel. That's where Quantum comes to rescue and identify eavesdropper in the channel. Yeah, that's pretty much I have for this demo. Thank you so much for listening in.
Thank you, Suresh and Enid. Just to stress that these testbed and tools presented today are available for external use and external parties. We would like to partner. There is a QR code, and you can go to research website of Outshift and then register to get access to that. With that said, I think we are ready to go for break. We have a break now exactly in 33 minutes or 15 minutes after hours, or in Pacific time, West Coast, 11:15 a.m. We come back and start our industrial session and the panel after that. I hope to see you after break, and thanks for being with us so far. Our next speaker is from Boeing. We have Matan Mohaber from Boeing. He is an applied quantum physicist, and also he leads the quantum networking program at Boeing. He is a PI or co-PI or lead in several flagship projects inside Boeing, like CQE mission and Q4S mission. Matan, please correct me if I am pronouncing them wrong. And he has led various quantum networking and classical laser communication effort in NASA previously. With that, Matan, floor is yours.
Thank you so much, Reza. I can confirm that everything was pronounced correctly, including my first and last name, which I sincerely appreciate. So with that, we're going to jump into this. Excellent talk by Kaushik, by the way. Really enjoyed that. And I'm going to pull on some of those themes in this talk here, which discusses satellite quantum networking, in my view, of what the next 5 years might look like. So first, we'll talk about how to measure distance. Okay, so we heard throughout the talks yesterday and today about quantum networks of different scales. This is a picture of Kansas that shows a fiber optic network. There's nothing to do with Boeing, just for example. And if you want to connect Topeka and Dodge City, the shortest path between them is that dotted red line, which is about 400 kilometers long, which is pushing the envelope of what a quantum network could support in terms of loss through fiber directly. But the fiber path, which is highlighted in the yellow curve here, the shortest path between those two cities goes through this dogleg path through the fiber network, adds up to about 700 kilometers of total distance, traversing 18 repeater nodes through that fiber link becomes harder. If there's some sort of network outage or maintenance, your traffic will be rerouted through the red pathway, for instance, in which case now you're contending with 900 kilometers. The longer you go through fiber, the more loss in the fiber you accrue through Beer's law, exponential loss. And this is the motivation why people are looking at other ways to transmit quantum information through a lower loss channel. The alternative being pointing two telescopes at each other and sending the photons out of one telescope and into the other. One can calculate what the relative efficiency of traveling through fiber across a certain length versus traveling telescope to telescope, or the free space optical channel across the same length. And it turns out that there's going to be a crossing point where the loss through free space is less than the loss through fiber. And so because of that, people recognize this early on in quantum network thinking and realize that space to Earth and Earth to space links might be necessary for creating long-range quantum networks at the scale of countries or continents. Certainly fiber-based quantum networking exists today. We see more and more demos of it almost on a weekly basis. I want to highlight two here, one connecting Beijing and Shanghai through a trusted node repeater network with each of those little bubbles is a trusted node repeater. And this is one highlighting work from Mehdi's company, who's going to speak in this session, where they established a teleportation network across the New York City area. And this is being expanded across Long Island. Plans were announced earlier in September. So very exciting things happening with practical, usable quantum network testbeds around the globe. Taking a step back again and looking at the space applications, there's a number of different specific missions that could be supported with quantum network in space, from the purely like communication centric, just sending quantum information around, to specific sensor topologies, like using quantum networks to enhance and secure distributed clock systems, using quantum networks to enable high resolution imaging of distant objects. So, sensing, communication, security, these are the motivations that have people interested in doing quantum networks in space. So to the best of my knowledge, these are the quantum networking missions that have been launched into orbit. Okay, so 2017, the China National Space Administration had Messius, which had a huge success in doing a variety of foundational, first of its kind demos from space to Earth. There have been some follow-up missions from China, the Jinan mission. Singapore had Spooky 1. I'm not sure about this, but it seems like in 2023 there might have been a Russian CubeSat for doing quantum networking in space. German mission Cube, Austrian mission QuickCube and Rocket, and Seek. This was launched last November, almost a year ago, where Boeing was involved with, led by Paul Kwiat from University of Illinois, that I'll talk about a little bit later. So this goes up to today, and again, based on my knowledge of the field, like what I see people saying in terms of missions that are launched with a publicized launch date or launch estimate, I list them here. A lot of stuff going on. Q4S, this is another Boeing mission, which I'll discuss in this slide deck, is on there. And these missions, they include multiple LEO missions, low Earth orbit missions, up to geostationary orbit, which is a goal of Spain. Very exciting stuff to come for sure. And I should add that every couple of weeks, a new mission seems to get announced. And so this chart will become more cluttered as time goes forward. So if I kind of look at it in terms of like what year it was launched, what it is, who is sponsoring it, the two American missions on this list are Seek and Q4S. I'm very proud to say that Boeing was involved in both of those as a supporter of Seek. We were just part of the team that Paul Kwiat led to drive Seek to orbit and operation. And Q4S is a Boeing-led mission that we're developing and is on track for launch next year. Looking at it another way, point out that most of these quantum networking space missions to date, and most of the ones that have been planned with the launch date in mind, they're QKD centric. Okay, so they mainly support quantum key distribution. I think it's worth pointing out that the two Boeing affiliated missions specifically go beyond QKD and into some of those advanced networking protocols that Kaushik just told us about. And then, a history of American involvement in satellite quantum networking. There's a lot of, I think, different information out there about what all has happened. So like I said, SEEK is in orbit, launched in November of last year. All mission objectives achieved. Q4S is on track for launch next year. Very exciting. IonQ announced plans to deploy a global QKD satellite network, which we'd love to hear more about those plans in the coming months. Before all this, though, back in 1999, there was actually a patent filed for performing secure quantum communication from low Earth orbit to Earth. And this patent was filed by a group led by Los Alamos National Lab staffers, including Paul Kwiat and others while he was working there. And kind of between 99 and 2024, that 25-year period in the US, there was not a mission of record for quantum networking in space. So that's changed. We have one in orbit now, one coming soon. In that intervening period, there was the Air Force Research Lab led a lot of foundational measurements of doing free space quantum optics through their telescope systems. And in 2021, there was an attempt, this CAPSAT program, to put single photon detectors into orbit, which unfortunately, minutes after the first turn on, it was hit by a radiation event, which caused memory overfill of the system, ended the mission early. So the SEEK mission, right? This is a photo of the ISS taken by one of the SpaceX capsules on approach to ISS. And in this photo, we can actually see SEEK mounted on the platform. It's there in the corner on what's called the MISSI platform operated by Aegis Aerospace. It's in one of these blue boxes there. SEEK deploys an integrated optical entangled photon pair source and bell test apparatus in orbit. Also, it has mechanisms to repair radiation-induced damage on the single photon detectors. And since launch, both of those systems have exceeded the design performance. And so we've met all mission requirements for SEEK. And in fact, the mission's been extended by an additional 6 months to continue to collect more data. And so far, from what we've seen in the literature, the entangled photon pair source on SEEK is the best performing source in space publicized to date. The next mission is Q4S, and with apologies to the audience, I am going to zoom through these slides a little bit. So Q4S is Boeing's a Boeing-led space mission with a team including HRL and University of Illinois. The goal of it is to perform quantum entanglement swapping in orbit. So in Kaushik's presentation, he mentioned the quantum repeater as being a necessary element of those future quantum networks. The entanglement swapping protocol that Q4S is going to demonstrate is a quantum repeater protocol. Okay, so the goal of this is to show that we can perform that operation in orbit under the rigors of the space environment in a way that's meaningful for those future space-based quantum networks. This is a diagram showing how it works. It's a cartoon in the corner showing what it looks like. I'm gonna zoom through this. Suffice to say, there's a lot of data from various test sources and test configurations that show the system performing well. Let's see. Looks like I've frozen a little bit. But if we could go to slide.
Makan, we lost your slide. I mean, we can see your teams.
Apologies for that. Let's see. Okay. So it should be back.
Yes, it is back.
Yeah. Yeah, apologies for that. So I want to land here, which shows some actual pictures of hardware, which I think might be interesting to see what it looks like. What does an entanglement swapping system designed to operate in low Earth orbit look like? This is a picture of our Pathfinder unit. So this is built as the flight system would look, and you can kind of see the general size and layout of it. This is a picture of the Boeing test facility where we can simulate the space environment. We put the whole assembly into a hard vacuum and can control the temperature to emulate what it might see in orbit as it passes in and out of the line of sight of the sun. And I'm happy to report that the performance of the system as built is meeting the mission requirements. And so we really are on track for that on-orbit demonstration in 2026. So this is a good thing. I'm going to skip this slide. So Q4S, we're going to do entanglement swapping in orbit. It's a good thing that's relevant to a lot of the advanced networking concepts being discussed in this workshop. Many other satellites planned for launch in the next 5 years, most of them focusing on QKD. We've had multiple institutions from IonQ to the China National Space Administration assert that they're going to deploy a global scale QKD network, including satellites. But there's stuff beyond QKD. And so I wanted to spend the last part of my talk talking about what else could be done. One is quantum teleportation. So far, none of those missions have performed teleportation between inertial frames because it's very hard to do that. This is when satellites are moving, photons are moving with respect to each other. This is the topology of what it could look like. We could teleport one qubit here to another photon there and do that in post-processing, not requiring any quantum memory. That's interesting. But if we want to do real-time teleportation and transmit quantum information across vast distances through this satellite network, like people have been saying in these meetings, we need a quantum memory that has a suitable hold time and efficiency. And so we can run some, kind of order of magnitude numbers to arrive at a rate at which this teleportation would be successful. And it does drive some requirements on how well this quantum memory needs to perform, how long it has to hold that quantum state. And so, we could think about these quantum memories, like Kaushik was saying, these are the ones based on atoms are inherently narrow bandwidth devices to achieve those long hold times. But there's all sorts of systematic effects that take place through satellite motion that would compete against that. We have Doppler shifts, effects of special relativity, and effects of general relativity that are all actually larger order of magnitude than the bandwidth of these quantum memories that would give us millisecond hold times. And so because of that, we really need to understand the kinematics and the relativistic dynamics of the system in order to use the quantum networks properly in this context. So it sounds hard, but really it's another version of the same problem that the GPS community had to solve in the 1980s and 90s. Also, I should point out that there are other ideas to perform quantum information distribution across planetary scales using methods that don't necessarily require quantum memories, but hold the photon in the sky for a long time without losing it. So interesting stuff. And I want to return to this concept of how to measure distance, right? Before I had the map of Kansas and showing the pathway through the fiber. If we're really honest about sending quantum information around a satellite network or up and down to Earth, we do need to account for all these relativistic effects. There's a great paper by Beauregard and Pekovsky where they talk about how that curved space-time, right? The mass distribution of the solar system creates the contour of space-time at which light travels. And so we need to account for that. In order to do photon coincidence measurement at these two detectors from these two sources, where one is deeper in the gravity well than the other, we need to account for that space-time curvature to line them up properly and achieve coincidence. And some of my own work deals with measuring the same effect using a distribution of Mach-Zehnder interferometers between Earth and space. So it's a lot of stuff, a lot of hardcore physics there. again, I think back to Kaushik's, one of his first slides where he's like, quantum networks are good for security and sensing and potentially fundamental physics. And so you might look at this and say, well, this is a physics experiment, but the reality is this is necessary knowledge that anyone serious about doing quantum networks in space needs to understand and needs to mitigate for in order to maximize the potential of that future network. It's an engineering challenge. So that's it. That's the end of my talk. What I want you to take away is that there have been a number of quantum networking space missions launched to date. Most of them have been very successful. Many more are planned for launch in the next 5 years. Most of them focus on QKD. On the Boeing side, we have quantum networking satellites and ground systems. I didn't get to talk about the ground systems, but that's okay. And our technology is supporting both QKD and the non-cryptographic quantum comm networking missions. I want to express to you Boeing's openness for collaboration and partnership for academia, private industry, US government, international. We're open to find the right partners to move this technology forward. And that's the end of my talk, Reza.
Thank you, Malcolm. That was a very fascinating and interesting talk with the challenges which hard to imagine. There are a few questions. I moved them to panel, but there is one question very specific to this, so I may ask you here. There's a question, is Boeing planning to install his own constellation for of satellites with this quantum for quantum networking? Or a question maybe comes follow up on that. Is the current constellation upgradable, or you have to do a new satellite launch and installation for all?
So what I can say is we're working with a diverse group of customers that's very interested in both of the ideas you just mentioned. And well, I can't make any announcements now. I wish I could say, I wish I could say something, Reza, but right now I can just say that this is something we're seriously, rigorously looking at.
So, but engineering and technology-wise, it's possible to upgrade current constellation. That's maybe a question to ask, or you need to definitely consider new installation.
I think it depends on the scope, right? And like again, I keep going back to Kaushik's slides because they were so good and clear. He talked about like quantum alarm and QKD and these different protocols. And there's different like barrier of complexity for those different protocols. Some of them are more compatible with maybe like upgrading a network to support that versus having to really start from the beginning to have that capability.
Okay. Oh,
I'm trying my best to answer your question.
No, I understand the limitation. Thanks for your presentation. Now we see you again in the panel for the rest of the question. We move on to our next speaker. Next speaker is the co-founder and chief science officer of QNet. It's a startup company. He is Mehdi Namazi. He has done his PhD in physics from Stony Brook University, and during his PhD has worked on the room temperature quantum communication and computation technology. Mehdi was awarded the Yale Joint Quantum Institute Postdoctoral Fellowship to work on novel quantum optomechanical system, and then after that he founded QNet. With that, I pass to you, Mehdi. The floor is yours.
Awesome. Thank you so much, Reza, for the introduction, and thank you everyone for having me and us here today. It's awesome to be here, and it's really fantastic to go after Kushek and Makan. I think they combined saved me like 10 minutes in the things I wanted to talk about, especially because I tuned this conversation and this talk to a project we are doing in New York City this year, which is actually on the side of entanglement swapping. To do in New York City. So it's very, very related to the past two talks that hopefully everyone listened to. But to just briefly talk about us, we are QNet. It's a quantum networking startup here in New York City with a major focus on figuring out different ways to deploy quantum entanglement networks. Without going too much into details, because Kushek extensively talked about this, we really believe in keeping all of our focus on entanglement-based quantum networks because of everything that we talked about today and yesterday. With quantum entanglement networks, you can do all the things that we know already about quantum networking, like QKD, secure communications, and key generations, but just much more robustly because of the enhancements that entanglement gives you. But at the same time, it gives you capabilities beyond just key sharing, quantum position verification that Kushek talked about it, or quantum augmented networks, which is the quantum alarm systems that came up many times. And more importantly, there are a lot of quantum networking applications with entanglement that goes beyond security. Again, came up many times today, high frequency trading, random number generations in a way that you can actually certify it and be sure that the numbers are actually random. And then in the long horizon of quantum networks, there is no other solutions for us to go over long distances and to be able to connect quantum devices to each other beside entanglement. We have just simply no other way to build quantum repeaters or distributed quantum computing. That's why at QNect, we are very focused in this idea of figuring out how to practically distribute entanglement. We are on the Earth for now. We don't do anything in space, so everything we do is fiber-based networks. But the part that we put a lot of focus on is the infrastructure. We try to build hardware that can be used for a wide variety of applications in quantum networking. So as we deploy these technologies out there, in 2 years, we don't need to go deploy a whole different sets of quantum entanglement sources, for example, for different applications. We can use the same devices as the different use cases and application of quantum networks expand at the same time. Now, to tell you a little bit what I mean by this infrastructure part and building something that can be useful, and Makan actually talked about this, also pointed this out, is that when we talk, for example, in a very simple example, if I wanted to build an entanglement source that is good for a distribution, all I would care about is three things. I just want an entanglement source that gives me a lot of pairs per second with very good quality and is compatible with telecom wavelengths because we work with fibers. And that's more than enough to be able to do entanglement-based QKD. But the moment I start thinking about what I could do beyond it, if I want to build quantum repeaters, for example, or quantum distributed computing and sensing, it is true that, of course, I need like quantum memories right now, or the quantum computers and sensors should interface with the network, but the requirement on the entanglement photons themselves increase significantly. Makan pointed out the first one, the spectral brightness. Now I don't just care about how many pairs per second I'm taking from like an entanglement source. I really care about the bandwidth of the photons, because literally all quantum devices, whether they're quantum memories, quantum computers, ion traps, neutral atom computers, these are atomic systems that can only interact with a few tens of megahertz of line width, but the vast majority of entanglement sources out there give you gigahertz, terahertz line width photons. So there's a factor of 1,000, sometimes 1,000,000 times mismatch between the photons coming from entanglement sources and what a quantum computer or quantum memory could deal with. Of course, you always need the high fidelity, but now indistinguishability becomes incredibly important, because every protocol for creating entanglement between computers or quantum repeating relies on interfering photons that must be identical to each other. That is HOIM, fundamental measurements, or entanglement swapping, or teleportation. All of them really care about identical photons. And that's not a trivial thing. Vast majority of entanglement sources out there, if you make 2 copies of them, they're not going to give you 2 identical photons out of them. We do need telecom compatibility, but now we also need to be compatible with the device that we're connecting to, whether it's a quantum memory, sensor, or computer. And then the type of entanglement qubit also really helps a lot, but I probably won't get too much into for this conversation. Now, this is a little bit of an example of what we consider moving more towards building networks that can actually be scaled up, whether it's in a city or whether it's in a quantum data center in the future. This is simply a HOM, measurements between 2 independent entanglement sources. Nothing new about this. Many research groups around the world have done experiments very similar to this. What we do differently here is the conditions under which we can get a measurement like this. For example, here, we do these measurements by just using off-the-shelf SPADs, so without needing to use nanowire, cryogenically cooled nanowire detectors. We can get these measurements by just using room temperature SPADs that you can just buy from DigiKey for like $2,000. And this measurements is compatible with White Rabbit, and the detector is jitter compatible without us needing to pulse the entanglement source. So we have the two entanglement sources are just CW free running, which if you happen to be a person who use entanglement sources, you know that there's always a massive advantage not to have to pulse your entanglement source. At the end of the day, a CW entanglement source is basically a pulse entanglement source with a pulse repetition of infinite. So it always gives you the maximum number of pairs per second that you could get, which really matters for us in the networks we build. But the problem with that is that then your photons need to be able to handle the jitter of your detectors, the White Rabbit jitters. And at the same time, we do these experiments without needing to do any laser sharings or frequency sharings between the entanglement sources either. Our entanglement sources by default are always indistinguishable. They always gives you the photons that are identical to each other. And everything we built so far is fully at room temperature. So no ion traps, no cryogenically cooled quantum dots, no trapped atoms, a fully room temperature system. And the reason we can do this, if you're familiar with our company, it sits at the core of our innovation, which is the entanglement sources based on full-web mixing processes in atoms. The detail of this doesn't really matter that much. These are highly bichromatic entanglement sources that they give you a pair of entangled photons, one at a telecom wavelength, 1324, the other one is 795 nanometer. We really like this combination because, as I was saying, we have to be mindful about being telecom compatible and at the same time compatible with our atomic systems. Recently, there was a lot of announcement about breakthroughs in quantum internet of making frequency conversion for telecom, for example, for ions. In our systems, we don't need that already because our entangled photons and entanglement sources, they act as frequency converters by default. And because we use atoms for photon generations, we can have a system that is simultaneously very bright and high rate, very easily out of the fiber into the entanglement source, out of the entanglement source. We can get tens of millions of pairs per second. But at the same time, these photons are very narrow-lined in frequency. We can bring down the bandwidth of these photons to around 250 megahertz naturally, which results in an extremely high spectral brightness, perfectly compatible with ion traps, neutral atom computers, quantum sensors, and of course, quantum memories for repeaters. We also get polarization entanglement for free because atoms really like to interact with polarization. So overall, we managed to get this system that gives us frequency conversion and frequency matching for free. The bandwidth really matters for us because what's narrow in frequency is broad temporally. So that's how we can handle the jitter of the detectors and White Rabbit jitter. And then lastly, because these are atomic-based systems and atoms are always identical, so are the photons that comes out of this system. So we don't even need to worry about indistinguishability. So that's why an experiment like this is possible, to have two entanglement sources, do entanglement swapping, and not worry about what type of detectors we're using. This one is a CHSH measurement of entanglement swapping. A lot of times, still for the telecom photon, we use nanowires just simply because nanowires have higher efficiency, so we simply get better rates. But for the ones that are the 795 photons, so the ones that are sitting next to the entanglement source, we have no reasons to use nanowires because SPADs at 795, 780 nanometers are very good efficiency, 65% efficiency, and they have very low dark count. So off-the-shelf technologies are very perfect for us. This matters for us because it allows us to think about something more scalable. When we deploy something like this in a city, we only need to worry about cryogenic nanowire detectors in one location. And as we increase the number of nodes in that city, or if this was a data center, as we increase the number of nodes between the different racks, now all the new nodes can just perfectly work with the SPADs. They can perfectly work for off-the-shelf White Rabbits, and they just share the nanowire detectors that was at the center location. If it's in New York City, it's going to be a data center. And if it's inside the data center, it's going to be a rack for these systems. So it allows us to think much more easily towards scalability of these networks, especially in a place like New York City that is significantly more crowded than more other cities, metropolitan scales that have so many different branches and locations that require to connect to the future in quantum entanglement networks. Now, we build everything ourselves. So it's not just the entanglement sources that we build. So I need to briefly talk about this, that beside the entanglement sources, we now, as a part of the entanglement sources, what mostly we offer are the Carina racks, which is basically a turnkey solution for entanglement distribution that includes the entanglement sources, as I talked about, but the laser systems for these entanglement sources. More importantly, because we use polarization, we needed to get very good at maintaining polarization in the single mode fibers, which is basically all the fibers in the telecommunication infrastructure. So the devices, the APC devices that we have in these racks allows us to start with something incredibly fluctuating and noisy. And when the devices are on, we can stay at very high fidelity with incredibly high uptime. And also, one of the things we had to get very good at is real-time measurements between remote locations. So being able to synchronize multiple racks with each other using white rabbits and time tigers to be able to do these measurements of which photon is entangled with which photon and how to do these measurements. These are part of the hardwares that exist together with the hardwares that we have from our third party. Like, we don't build time tigers or white rabbit ourselves. We just add the software suite on top of these systems for everything to work together very smoothly. We have a testbed here in New York. We call it Gotham Cube, where we do a lot of our testing here. And one of the things that mattered to us the past 2 years or so was to simply show that we can distribute entanglement at high quality, but with very high robustness. Because that was not a given. Really do entanglement distribution with high quality, fragile, and hard to deal with, but we didn't know how it would act when we interface it with real life infrastructure
Mehdi,
in a noisy city like New York.
sorry
Yes.
to interrupt. Your voice get distorted. Maybe you want to repeat the last 10 seconds.
Oh, okay. Yes, sure. So this experiment is published last year of showing how stable the point we got in distributing entanglement, especially in a city like New York City, but with very high stability, because that was also not a given thing about quantum networks. And this is an example of the data in that paper that you can find of doing 15 days continuous entanglement distribution with very high rate, with maintaining the polarization end to end at the maximum level possible for this experiment. Without us using the compensation, the polarization would have been fluctuating all over the place. But then the purple line is us doing the compensation, and more importantly, showing that the system was fully automated with a network uptime of 99.84%. Not even a single second in 15 days we needed to touch anything manually. To show for the first time that entanglement networks are now can be automated, they can be 24/7 operational, and the user, can tune them based on their application. You can have something with very high rate of even 500,000 pairs per second after 18 dB of loss. That is more than enough for a city like New York, but it's still within security bounds, for example, for QKD. Or you could do even end-to-end 99% polarization fidelity, which back then, and I still think is the record for polarization distribution in real-world fibers. We do a lot of the work now. This paper just got accepted in GOCN. We do a lot of our field testing collaborations with Deutsche Telekom in Berlin. So these experiments are very similar to what I showed you, with the difference of doing the experiment over 100 kilometers of fiber versus 34 kilometers, and interfacing it with much more real-world telco infrastructures, because Deutsche Telekom has much more hardware than we do have for the classical side of the house. For example, this is a data of propagation, but co-propagating with classical light on the same fiber and still maintaining very high fidelity non-stop. That's one thing we benefit from because of our wavelengths. I'm going to jump over this quickly because I'm pretty much out of the time. I just want to point out that another advantage of using entanglement sources like ours, which are atomic systems, is not only the entanglement properties themselves are very good. For example, we do a lot of experiments for towards quantum repeaters, interfacing them with quantum memories who are also rubidium based, but also these can be used as squeeze sources that are very useful for quantum alarm systems and tap detections, and also frequency conversion, for example, for connecting quantum computers and so on. So the same atomic system can give you multiple different use cases beyond just entanglement devices. We are here dominantly in New York City, but very recently now we are opening a branch also in Albuquerque to create a fully open access testbed there for everyone who wants to work with us, but also use these hardwares and do test use cases and developments on the network like this. So if you're interested in doing experiment with these devices, please do feel free to reach out to me. And yes, this is us. Thank you so much, everyone, for listening.
Thank you, Mahdi. Was very good presentation. There are a few questions. Some of them are specific to you. I asked them here. The rest, which is more general, I leave it to panel. For your system, what is the bandwidth you need to allocate, basically isolate for your quantum channel when you co-propagating with the classical channel?
Well, our photons are at 1324, so when we co-propagate, we can use all the bandwidths at 1550 because we don't have anything there. If we are using it ourselves internally, we can have, for example, all the white rabbits and all the synchronizations for like polarization, compensating, and everything around the 1550 lines from all the channels of the WDM. It doesn't matter. 1550 is far, far away from 1324. And an advantage of narrow lined photons is that it's much easier to filter out even if any leftover Raman noise there. We still haven't tested to see what's the max amount of noise it can handle. So how much we can saturate the 1550 bandwidths until there's too much noise. But so far, we barely see anything on 1324, to be honest.
Okay, great. And another question, when do you expect your repeater to be available and deployed?
That's a much harder question. Yeah. Yeah. So we, around a year ago or so, we had 2 years ago or so, we had a little bit of change in strategy. We are working very heavily on quantum memories, but the memories we're working at QNX are room temperature rubidium based because we really cared about being able to build something that has the quantum performances, but can also be deployed out there in rack systems, in fiber hubs, and so on. And that always means much more promising future if it happens, but a slower progress because building things, quantum technologies at room temperature are much harder. And that's one of the reasons we are at the same time focusing a lot on the use cases that we can do for data centers or metropolitan scales, because these distances we're talking about doesn't even require quantum memories, and a lot of applications we're working on, we can pull it off without having the quantum memories while we're building the repeaters. So I would say it's still reasonably a practical quantum repeater is within 5 years or so away, because we also care about having a realistic rate out of a repeater that someone can run a protocol on top of it.
Thank you. Thank you, Mehdi.
course.
Now we are moving to our next speaker. Our next speaker is from Oak Ridge National Laboratory. We have Nicholas Peters. He is a section head and distinguished researcher staff in RNL laboratory. He leads the quantum communication team there, and he has done many pioneering contributions in quantum networking. And he's a member of the American Physical Society, member of the Optica, senior member of Optica, and senior member of IEEE. With that introduction, Nicholas, I leave the floor to you.
All right. Well, thank you very much, Reza, for that introduction. It's my pleasure to be here and to follow such distinguished speakers covering a lot of topics that are very interesting to me. So today, with this just short period of time that I have to share, I will share some of the work that we've done in our quantum test bed. And we're a research organization. And so our goal and vision is to enable the ability to network quantum devices to scale quantum advantage and enable new science. So that could be distributed computing. It could be computing between racks of quantum computers, or it could be in quantum sensor networks. So one of the most interesting things about quantum networking is that if we do it right, it will be something that will be flawlessly underneath the capability that everybody appreciates, much like, current telecommunications networks and your phones. And so that's really what we want to enable. We want to understand the science to make this reliable and scalable. But right now, there are a lot of different competing technologies out there, and it's not clear which one of these technologies we want to use. And if we think about how telecom networks have evolved, we don't necessarily have to have one technology to do what we want, right? There may be a number of technologies that will compete and coexist as we build out these research networks. And so that's really the thinking behind some of what we've been doing in developing our test bed. So our test bed is designed to be something that is more than just the hardware. It's designed to be something that takes advantage of all of the people and the hardware expertise in order to do things and test things that people can't currently do. And so the idea really is to build a test bed that enables the discovery of new ideas, developing new protocols and applications, as well as solving some of the fundamental challenges that we have. And two of the biggest challenges we have are mitigating decoherence and dealing with the loss that we have in the transmission of quantum data. So if we think about it more in the context of quantum data, we want to have quantum data so we can build these large-scale networks of computers and sensors. I mean, that really enables a lot of the capabilities that the applications that people talk about that they want to do. Okay, so just a quick overview. So I lead the quantum information science section. We currently have 3 research groups. Those research groups are basically mostly comprised of staff, so they're all independent PIs. So we do many more things than I'm going to touch on today. But some of the things that I won't touch on other than in this overview could in fact play a major role in scaling quantum networks. So for example, we have several people working on calcium-40 ion traps, and that's something that could be used for building quantum repeaters. We also do a fair bit of work in squeezing that uses rubidium-4 mixing, which is a sort of natural connection point to what Madi's to the previous talk. But for the quantum communications work, we specifically have about 12 full-time equivalent of staff from across the laboratory and about 5,000 square feet of dedicated lab space. And one of the things that's been exciting but also challenging in the past this past summer is we moved into a new research laboratory. It's actually a suite of research laboratories. When you do that, you have to shut down all your experiments and move them in, and hope that things are still working when you move them in. So that's an ongoing process. But we're hopeful that that process will lead to us being able to do experiments that we couldn't previously do. So even though we've moved into this special lab space, we're very focused on deploying and demonstrating things where they are done in a distributed fashion, which is actually a lot more difficult than just simply doing things all at one optical table. So at ORNL, we've been building up our quantum networking capability for a number of years. And sort of our first big experiment we published in 2021, and there we were really focused on building a local area network, in particular demonstrating the utility of using wavelength selective switches for flex grid entanglement distribution. And in addition to that, we made the first network demonstration of the protocol remote state preparation, which is similar to the quantum teleportation protocol, but a little bit simpler. And then building on that network, we heard about White Rabbit in the previous talk. What we did was we showed that if we can take White Rabbit and improve our timing distribution on the network, what we can do is we can narrow down the coincidence windows that we're looking at where we collect the entanglement that gets distributed. And if you can narrow that down, then basically you can get more signal and less noise. And so that enabled us to improve dramatically the fidelity of the distributed entanglement. So building on that work, the idea is we want to move beyond local area networks and enable eventually wide area networks. And so with that in mind, we've been building a capability not only from a node standpoint, but also in terms of an infrastructure standpoint of the quantum network. And so to do that, windows that we're to do that, we've deployed fiber in loops that go around this lower left-hand side here, so that we can get up to 300 kilometers of deployed optical fiber to test the technologies that we're developing, as well as the protocols. And to Makan's point, because we have exponential fiber loss, in the near term, we do expect that if we want to have large-scale quantum networks, the best way to do that is to use satellites. And so we're also developing a satellite tracking optical ground station. And so at left here's a picture of an example telescope. It's not the one that we have, but we're building an optical telescope, which will be, it'll actually be sited on this map that I show here on the right, but not necessarily where this arrow is pointing. But it will be connected to our fiber network. And so we'll be able to collect and transmit photons through this low Earth orbit satellite tracking ground station and send those to our laboratory space. And so since the TRC building is new, it's not actually shown here on this figure up at the top left-hand side, but we're working on getting that fiber connection, and we're working on building this satellite tracking ground station. And eventually we'll have the local area network, this long fiber network, and our satellite network all connected via transparent optical switching so that we can test a variety of different technologies under different conditions. And so one of the things that's really critical to this is understanding all of the errors that you get. And some years ago, we studied that in the context of doing quantum key distribution, and it showed that Raman scattering is actually a pretty big problem if you're trying to integrate classical communications along with quantum communications. And so, one of the things we're doing is we're trying to understand exactly what all the errors are and how best to mitigate them. That's going to be key towards viewing and utilizing quantum communications from a quantum data perspective. Okay, so what are the things that we can do in the laboratory and what we can do with light in general to help us mitigate the problems that we have, the challenges that we have? So one of the, I think, most attractive ideas out there is to utilize this idea of hyperentanglement, which is really that, the photons are the things that get lost when we transmit light over optical fibers or free space channels. And, if we can send more entanglement on a pair of photons, then when the photons make it, maybe we can utilize that entanglement and we'll have some advantage because we'll have multiple e-bits of entanglement, and we can use those in future protocols. Now, the second idea here, and captured in this slide, is that if you build an entangled source right, you can build it in such a way it generates entanglement over lots of bandwidth. And so we can have many, many channels of entanglement that get distributed from a wavelength channel perspective. And this is maybe a little different than what you would do in a classical network, because in a classical network, you have to worry about nonlinear optical effects from having classical channels propagating on an optical fiber too closely spaced. But we don't see a lot of impairment from sending too closely spaced single photons. And so we can actually fill very many optical channels, and we've demonstrated with our sources the ability to build up 150 entangled pairs worth of optical channels in this C and the L bands. And so when we do this, we can treat both the polarization and frequency degrees of freedom as distributors of entanglement. And shown at the bottom left-hand slide is what we call the tomographies of both the polarization state and the frequency state. So one of the key pieces of technology that we've developed at Oak Ridge National Lab that allows us to do tomographies on the frequency domain is the idea of actually using frequency as the degree of freedom to do linear optical quantum computing. And so what we can do is we can do the gates that are required in quantum computing, and those gates in combination with projection and measurement allow us to do projections that can characterize fully these different frequency states. So normally people work really hard, and it was mentioned in an earlier talk today, you try to remove the frequency degree of freedom entanglement if you've got polarization degree of entanglement, because if you're trying to do things in polarization and you also have frequency, it messes up your ability to do the polarization well. But if we can actually manipulate the frequency, maybe that allows us to utilize that extra entanglement instead of it being something that messes us up. So one of the other nice features of using the frequency degree of freedom is that we can actually use multiple levels. And so as an example of that is a tomography shown at the bottom right-hand side, where we have frequency qubits and we have frequency qubits that are entangled. Okay, so how do we manipulate both the degrees of freedom at the same time and do something quantum? Well, it turns out we can do a controlled NOT gate between the different degrees of freedom using these electro-optic modulators and this frequency processing technology that I just mentioned. And shown at the left is sort of the truth table that you'd expect to see from one of these controlled NOT gates. And down on the right-hand side, this is the sort of proof of that you can use this controlled NOT gate to generate entanglement. Not just generate entanglement, but you can generate any of the Bell states, which is actually what you want to be able to do. So less interesting, but you could also use this to disentangle the frequency and the polarization degrees of freedom. And the idea is that if we can then manipulate both of these degrees of freedom at the same time, then what we're working towards is building up the capability to take these two different entangled resources, manipulate them, and do entanglement purification protocols by using hyperentanglement. So that would be something that we would really like to do, is to efficiently take ensembles of entanglement and then to correct for the impairments that we get from transmission. Okay, so in addition to that, when we look at the technical details of doing this sort of distributed frequency processing, it turns out that being able to have very, very tight synchronization is really important, because we're using electro-optic modulators and they have to be driven with RF sources, radio frequency sources, and we have to have very good synchronization between those in order to do the types of operations that we want to do across large scales. And so to do that, we've developed a radio over fiber system that's a home built system to get sub-picosecond synchronization. And with that, we're able to take our entanglement, and so this is frequency entanglement, and we can see the joint spectral signature here in the middle of the screen. So what that says is if I measure one idler, I'd expect it to be very strongly energy correlated to its corresponding signal photon, which is what we expect from energy conservation. And then if we send that entangled pair down our network, and the phase is not correct when we do the analysis between the analysis of the phase modulators, then we see a spread out joint spectral intensity, right? So we lose our correlation. That's the signature of energy entanglement. But because we have excellent timing synchronization, we can actually do the what we call non-local modulation cancellation of the frequency band entanglement and recover that strongly energy correlated joint spectral intensity. So we've got one more example here where we can mitigate classical crosstalk using what we call percussive filtering. So this is a process where, knowing something about the errors, you can apply a local filter. And so in this concept of operations, the idea is we create entangled photons and we mux them, we multiplex them into two different optical fibers along with classical traffic. So classical traffic, in this example, we consider it to be polarized. And so that polarization of that classical traffic is many orders of magnitude stronger than the quantum traffic. And what it does through the naturally imperfect filter isolation from our multiplexing and demultiplexing filters, what it does is it shows up as noise in the off diagonal, or it can show up in the noise of the off diagonal of our entangled state. And what that does is it reduces the quality of the entanglement that gets distributed through the network. And so what we can do is we can realize that we can add local filters, which will preferentially reduce the noise term. It reduces the entanglement intensity, but the idea is to reduce the noise at a faster rate than you reduce the entanglement intensity. And so therefore you can take an ensemble of noisy entangled photons and create a smaller ensemble of more highly entangled photons, which is a very highly desirable thing to do. That's sort of the intent of building quantum repeaters. So I'll just go to this example here, and this is a network example. And the experiment's shown on the left, and we did this over our Orano network. And the middle plot is the thing that's kind of the thing that you want to look at here, plot A. And we start out with an ensemble that we measure in the entanglement fidelity. The entangled state fidelity is about 80%. So that's basically something that's not useful to do something like, say, for example, quantum key distribution. And by applying our local filtering, what we can do is we can reduce the throughput, which is shown in the plot immediately below. So we reduce the throughput, and for some cost of reducing that throughput, we can improve the entangled fidelity. And so we can go from some fidelity that's about 80% up to fidelity that's about 90%. So in this particular instance, you can go from a case where you couldn't really do quantum key distribution at all to a level where now I've got an entanglement ensemble. After distributing it across the network, we can apply this filtering and then get a resource that is then useful for doing a protocol. So that's actually, I think, a pretty big deal. And I think that's the first time that that's certainly been done with procrustinating distillation. And so you can kind of see graphically on the right-hand side how the entangled state looks. So we have this noise here that's from crosstalk, and applying our local filtering reduces that, and we get a state that looks more like the Bell state. So the final thing that I wanted to mention is that I've talked all about qubits so far, with the exception of that brief mention of qtrits, but there's an entirely different paradigm that utilizes continuous variables. And this is where squeezing comes into play. So squeezing is very useful for quantum sensors, and it's a continuous variable, so it's an encoding in amplitude and phase. And we've done an experiment where we can take squeezing and distribute it along with classical traffic, a bright laser for the local oscillator, which is used in homodynamic detection, which is a little different type of detection than is ordinarily considered in the context of quantum networks. And this is a fairly complicated experiment, but all of these parts are actually needed. But it is just the very first one, and it goes back to a point made earlier, which is it's really important to be able to do these quantum protocols in a distributed fashion. And so in this experiment, we start with the source, and we generate two-mode squeezing. We distribute it across the network, and then we have two independent homodynamic detectors where we're able to measure this squeezing jointly in different locations. And so this is shown on the left-hand side, basically without any sort of impairment at 0 kilometers, and we have about a dB of squeezing. And when we send that squeezing across our campus fiber, along with our classical signals, as well as a classical signal to distribute our radio frequency over fiber, as well as our local oscillator, we can show that we do in fact get squeezing that's statistically significant over this distribution. And so this is the kind of thing that you need to be able to do first if you're going to build a quantum repeater that's based on continuous variables. And the reason why that's interesting is there's at least one company out there that's trying to build quantum computers using continuous variables. And the more we think about it, the more attractive this idea of building up quantum repeaters based upon quantum error correction codes. And in particular, there's a certain kind of quantum error correction code, the GKP code, which utilizes these continuous variable techniques. And we're working towards building this. And this is all at telecom wavelengths, so you don't have to do frequency conversion. Okay, so with that, I'm done. Thank you.
Thank you. Thank you very much, Nick. That was a great presentation. I guess we move on in interest of time to panel, and then we ask all the questions in the panel. I would like to ask all the panelists to turn on their video, and I asked the question, and also for audience, my colleagues are monitoring the Slido. If you would like a question to be asked to the panel, if you type it there, they will categorize it and communicate with me so I can pass it to the panel. So with that, let's start with the question that we have so far. So I am sure you guessed this question, but in your opinion, what would be the killer classical application? Forget about the quantum computing application, the killer application in other domains for a quantum network, or in particular quantum entanglement network. And that's a follow-up question to that. Is there any existing customer or user or application that doing that beyond the experimental in the lab? So I start, randomly each time. So I start from Makan.
Great. So the question was, what would be the killer
Application for
non-quantum
quantum network, yeah.
application? Right. I think broadly speaking, to me, that would be having a communication means where you have some level of certainty of who you're actually talking to. I think that authenticity and verifiability of an information source or a communication partner is a problem with our current digital networks, and potentially some of these quantum protocols could give us a mean to add a layer of trust to our interactions. And so in terms of like specific quantum stuff that gets at that, I would actually look further back even before QKD to like the quantum money kind of ideas that underpin that kind of transaction.
Thank you. Ramana?
All right, my random number is 2 then, huh? No, I think as I talked about it by keynote, right? I think entanglement and no cloning are the two main drivers, right? So entanglement, we are furiously building entanglement-based quantum networks. So, and entanglement will be distributed, and if you can leverage that to Makan's point, right, and maybe authenticate or make sure that like you have some sort of end-to-end protection of your communications, either in the form of like some of the things that we talked about, like eavesdropper proof, security detecting people who are mucking around with like or tampering with signals. I think that could be a good use case. Now, whether it's used for identity establishment, end-to-end encryption, or just like point-to-point link protection, I mean, those are all nuances, but I think that would be to me that has got the most I would say potential for transformation, because it's a here and now problem. Like I mentioned, right, like quantum computing is going to affect our cyber infrastructure, and if we can leverage quantum to actually protect against quantum threats, I think, and given the amount of like established fiber that is out there, I think it's going to be a game changer, and that I think is the more near term. But then applications like decision coordination and secure position verification, these are definitely there. Time synchronization is another one with a huge potential. Now, White Rabbit is there, but like I feel like maybe if we can actually come up with some sort of time synchronization mechanism leveraging entanglement, that can actually like open up a lot of doors, especially within data center and across data centers. So yeah.
Okay, thank you. Okay, Kaushik?
So for me, it's more like, okay, so whenever we talk about the quantum network and applications of quantum network, we have to compete with the classical counterparts as well, right? Like, so we need to come up with some killer app which cannot be realized by just using classical information. So that's why, like, I try to be like, yeah, like as Ramona said, like those alarm and QPV, those things are like cannot be realized just using classical information. So these things could be interesting. Another one is that also like the time synchronization and all those stuff, because lots of in finance, like trading applications, like the time synchronization is quite important there as well. So I would consider those things, and also like these time synchronization, it's not something security related, so it's much easier to adapt as well. So I would go for this thing.
Okay, thank you. And Nick?
Okay, so I think this is maybe not necessarily probably what you're thinking about, but in my mind, one of the greatest impacts is going to be if we can develop classical technology to be quantum limited, that's going to have a huge impact on the energy consumption of networks. Because if we're using less energy to detect things because our detectors are fundamentally limited and can see quantum signals, that means we're going to have to use less energy to power all those things. We're going to have less cooling, and we're going to be able to shrink things down and deploy it more widely. So I think that's going to have a huge positive impact. And even though it's not necessarily a direct quantum protocol, it will be a direct application of us transitioning our ability to build quantum grade devices.
Okay, Matthew?
It's such a disadvantage to go last. Like, I think I want to like, yeah, no, I think one of the things I think about more and more, and everyone pointed this out, especially Makan and Kushik, that like for a while, this Q day was very famous in quantum community, the day that quantum computers can break RSA codes, which like you would need quantum networks for, but classical networks had a solution for it, post-quantum encryption. Exactly as Kushik said, there was other ways you could figure that out. The one thing that I'm more worried about than quantum computers nowadays are deepfakes and all the ways that you could pretend you be the end node person, and like there is no way for classical networks to verify the authentication of the person when deepfakes get perfect, and we're not far from that day whatsoever, like currently. So protocols like quantum position verification really allows you to know you're talking to the bank branch, to the secure locations, to the defense organization that is calling you, or especially for much more critical applications. So, and then I really personally don't know if there is any solution but to just do these things at quantum.
Great. And Wolfgang, sorry, you are the last.
Many important things have already been said. So from my fundamental research point of view, I expect great challenges that we can solve with time synchronization and enhanced phase synchronization over a global network. That would be most beautiful, and I think it's a valid driver of it. But also from my quantum position verification side, as far as I see, there might lie a real quantum advantage because position verification is impossible classically. And if you believe in post-quantum crypto, then quantum crypto is not needed. I have to agree to.
Okay, great. Thank you. And then another question also we have from audience is, do you see that we're going to have a single network provide entanglement as a service like maybe we saw from Deutsche Telekom, for example, an operator provider, and the enterprises build the application on top of that, or you see a dedicated network for individual applications? Anybody? Makan, I can see you are volunteering to answer first.
Just trying to look smart, but I'm nodding in agreement to that great question. But yeah, I think that it's likely to be a diversity of different types of quantum networks for different length scales. Just like we have different networking capabilities, right? For like Wi-Fi and Bluetooth and these internet protocols, and they all exist to support different length scales of digital information communication. I think it'll be kind of similar for quantum. That would be my guess.
Mehdi?
Yeah, no, I totally agree. And I think it also always depends on the company and entity and the regulations in that location. Like I know, for example, Deutsche Telekom cares about like random numbers as a service, because there are a lot of regulations in Germany that actually cares a lot about authenticity of random numbers. So it makes sense, and it has to come from a third party. So it makes sense that it be provided as a service through telcos for like different like gaming industries, for example. But then, like, for example, in a case of like adding quantum capabilities to data centers, it would be definitely something that Cisco would want to do more than any other company out there. So these things gonna be very application. And like if it's quantum position verification, then all parties need to have a hardware, like a version of a quantum modem or something in their location anyway. So it has to be deployed.
Okay. Anybody wants to comment?
Yeah, so I have a perspective here. So I think the way to think about it is, just like we have, end-to-end links and, links and end-to-end paths, right? Interconnecting nodes and that are operated by different operators. I feel like, entanglement is one of those things where I think it will become a utility that is not controlled by any one entity, but it will be like, a series of like autonomous systems that will probably distribute entanglement at some level. But once you distribute the entanglement, right, between Alice and Bob that are located halfway across the world, your applications can be built on top, right? So that is the end-to-end principle, right? Like, because that is the medium on which your quantum information is actually going to be either transferred or exchanged or used in some meaningful way for your particular application. So I would see that entanglement itself is not going to be, or entanglement distribution network is not going to be on a per application by application basis. I think it'll be a utility that anybody can tap into and build their applications on top. Now, Mehdi raised an important point, right, which is basically there's sovereignty requirements around quantum random number generators and maybe other types of like, especially when it deals with privacy, authentication, these types of things. There may be some restrictions around which vendor you actually buy your hardware from and which vendor will be compatible with which other vendor. I mean, those are all more from an end host or a node perspective. But the network itself, I think, is going to be operated by many different entities, and they will all come together to provide that end-to-end entanglement distribution as a service globally.
Okay. We have a lot of question ideas. If I want to go to everybody, we're gonna run out of time. So any comments on this topic?
Just to end, like, I mean, I think from an application layer point of view, I mean, again, as an end user, I don't care like how the network is built, like all the physical layers and all those things. I just want to make my application and run on a quantum network. So that's like from the end user point of view, that's the like ultimate goal. If we make a quantum network which is like more or less abstract away what is happening with the lower layer, then that's perfect.
Okay, now moving to next question. How critical is memory? Can we do anything beyond QKD without the memory? I mean, who wants to pick up first?
I can go first. No, we can do a lot of things without memory. Really depends on the distance, and like hopefully by early next year you'll see a lot of the experiments we are also doing. And I say that as someone who got his PhD on quantum memories, but there is like that's because that's part of the things we try to do. I love quantum memories, but even if when you have quantum memories, because they're sophisticated, they are expensive, they are hard to maintain. We always want to think about, okay, what are the use cases you could do without quantum memory, even in like metropolitan scales. So they will be much more practical for deployment. And then you only use quantum memories when you actually have to. That would be like distributed quantum computing or like blind quantum computing, places like this. So a lot of these protocols that were like basically a lot of the things we talked about, quantum alarm, QPV, random number stuff, none of them really in principle need quantum memory. You usually need memory when there is the buffering, like with the quantum computer stuff, or obviously the long distance communication. So I feel like as long as things are staying in metropolitan scale use cases or data center use cases, the distances are manageable. We could get away from a lot of things with a lot of things that can handle quantumness without memory.
Any other comments?
Sure. I'll just comment that a lot of times when we're building quantum communications protocols, there is this idea that you need to have some kind of classical signal involved, right? And so, if I learn something based upon a measurement and I want to use that, I'm going to have to delay things. That's not strictly speaking a quantum memory. And especially in the context of telecom networks, we can use delays of fibers. It's not as elegant as using a straight up quantum memory, but that's going to allow us to do the processing on the measurements that we make in order to feed forward the information in order to affect the whole quantum protocol. So it is important to remember that we do have tools in the toolbox that we can utilize.
No, that's a very good point. Yeah. If not, there is one more relevant question. So the question is that do we need to build a repeater to get a distance, or we do the satellite and a combination of the satellite and fiber network? So we established that memory is not essential for the classical application. Then if we remove the need for the distance by satellite, then means that we can do a classical application, support a classical application without memory altogether.
So maybe I could take this one. So, or at least I'll start us off. So the reason why we want to have a quantum repeater is because there's this idea. I mean, it's a fundamental limit, right? So if we have a certain amount of loss, there's a maximum amount of quantum communications that we can do. And
Yes.
initially that was discovered in the context of quantum key distribution, and then it was generalized. And so if we want to have satellite networks, they will allow us to do certain things, but they will not necessarily allow us to do certain things at the rates that we ultimately want to do them, right? And so as we build and scale networks, we're going to need higher capacity, and that's why we need to have quantum repeaters. To start with, it's very important to show that we can move from what's classically possible to what's possible only with quantum. And that is what a satellite network is good for, to span the vast loss associated with large scale distances. But ultimately, we want to have quantum repeaters so we can scale this up and democratize the distribution of quantum data.
Okay. Anybody wants to comment? I don't know.
I guess the only thing I would say is, just as classical internet, I mean, there's no one technology, right? Like if you look at the end-to-end path, it's stitched together from many different, segments. You have Wi-Fi at the edge, you have copper in the form of Ethernet, and then you have long-haul optical fibers, you have microwave. I mean, all types of technologies are out there. So, it's not like a either or. It depends on how far you need to go and what type of resources you have access to. And if satellite becomes offers the dollar per, the cost, it's a trade-off between fidelity, cost, and the rate at which you can transfer information. And if that's the economics that works out, that's available to you, and that's what you rely on, right? Eventually, I think a lot of it has really boils down to, I mean, as Nick mentioned and other folks mentioned, right? There's just a bunch of technologies out there, and that offer different price points and fidelity and efficiency trade-offs. And what will win is really, dictated by all these economic factors and what is available for you, right? Like to Kaushik's point, I'm not wedded to where my entangled photon is coming from. It doesn't really matter whether it came through an undersea cable or through space or to terrestrial fiber. All I want to do is basically the lowest cost, highest fidelity, good enough for my application. I'm good to go.
Yeah. I don't know, Markan, do you have a view on that?
Yeah, I think it also depends on the opportunities where to, for instance, put quantum payloads on satellites, like the upcoming European satellite network has a dedicated quantum payload. And so that makes sense, therefore, to strive forward, also to implement satellite-based quantum interconnects. But at the same time, of course, develop quantum repeaters, which in the end also should be on a satellite. However, the complications, they are tremendous for the time being. So I think going in multiple directions is the only way to satisfy the need of many people for remote entanglement.
Great. Now, another question is that yesterday, which was about quantum computing, the summit focus, and you can see in a lot of conferences you go on quantum, when the computing comes, a lot of attention was on error correction. Now, in this context of this summit today, this day, which is for classical application, how error correction is important and what is a pathway toward that. I didn't see in any talks today that this particular aspect of how we do the distillation, entanglement distillation or correction within context of application we discussed today. So maybe start with Wolfgang from academic point of view. You are muted, Wolfgang.
Oh, sorry. You were referring to me. That's a very complex question. And probably I would compare traditional ways of quantum repeaters to photonic quantum repeaters, a concept that not so long ago was put up and compared regarding the numbers and fidelities in remote entanglement bit rates, EBITs that can be generated. And the case, I think, is by far not clear yet. So because that's a advanced way of doing entanglement distillation, basically. Yes, so as we have seen today in presentations, there was talking about percussion entanglement distillation and methods and running error correction codes over the qubits that are received. And I'm not the expert in the field, but I guess a combination of error correcting codes will be the way of achieving entanglement distillation. I guess remote error correction codes.
Okay. Yeah. Anybody wants to comment on this?
Yeah, a little something. I mean, you know, we got to say, I think in like Nick's presentation, he talked about the group at Oak Ridge and all the different things that they're doing that touches on quantum. And certainly at Boeing, like I represent the quantum networking side of Boeing. There's an even bigger team that looks at quantum computing and algorithm development and stuff. And so it is interesting to look at the interface between these two different quantum fields. And oftentimes in an academic sense, those interfaces are not fully explored, right? But then when you go into industry, you're forced to be in that middle area, right? And that goes exactly to the question that you asked us, Reza, which is like, how does quantum error correction come into play in these quantum networking ideas? If you're really trying to network quantum computers, you know, where does the code come in and how is it used? I can just say that from Boeing, that is a question that we're looking at very seriously and devoting a lot of our resources to try to understand that, right? So I can't say more than that, right? In like publicly about like what specifically we're doing. But I would point out that Nick also had a good point about hyperentanglement and using those higher dimensional quantum states, that in any networking application, you're limited by loss. And so the more information you can put on a photon, the better off you are, you know, at a high level. And I think also that might even simplify some of the receivers that you use and how they're laid out. So a lot of value there in using hyperentanglement.
Any other comments?
So, you know, yeah, I do have some thoughts here. So, so the way I look at least like in the analogies with classical networking, right? So you have, you know, error detection, error correction, error, like all types of like, you know, error mitigation techniques. And what you use is really dependent on your noise profile and, you know, your sensitivity towards your particular application and all that stuff, right? So, you know, somewhat tied to the particular application. I mean, in at least classical world, I think at the end of the day, your goal is to transfer one bit from, you know, location A to location B reliably, okay? And it's because it's actually traversing many different hops, and you apply different types of error, you know, detection, and it could be end-to-end response, or like, you know, it could be local error correction. I mean, a combination of techniques to actually get your bit reliably from place A to place B, right? Now, it depends on your application in the quantum arena, because if you have a quantum key distribution type of an application, maybe it is less sensitive towards errors, right? A few errors is not going to like, you know, really doom the application. But if you go to a data center and you have distributed quantum computing, if you don't do error correction locally for every and high highly redundant, error correction, right? Not just so that is very important because you have partially computed your circuit on one processor, and it would be a shame to lose all that computation just because you're doing this gate teleportation or qubit teleportation and you encountered errors, and then the whole circuit is doomed, right? So it depends on the importance of the information that you're actually transferring, and that's where the techniques come into play in providing that additional redundancy so that your end-to-end application performs the best. So bottom line, I'm saying there's no one size fits all, okay? So there's no need for us to keep packing error correction at the entanglement distribution or the network layer unless it is universally applicable for all applications, in which case you shove it down the layers, right? But if it is actually very different for different applications, then it makes sense for those applications to independently figure out how to actually do error correction and on what links and at which location and what type of techniques, right? So this layering argument, I mean, just analogy from classical networking, right? The layering is all about figuring out commonalities across applications that you want to shove it down the layers. And if it is something bespoke for different applications, you keep it application specific. And that's the philosophy I would see playing out in the quantum arena as well.
Great. Now we have two more questions. I think we're going to run out of the time. Already we are running out of the time. So one question is, I guess, goes for Cisco, Ravana, Kaushik, and Mehdi, and to some extent maybe Makan. When you expect to make money, or when do you expect people pay for a quantum network to run an application? In terms of a timeline, that's a timeline question. I start with Kaushik.
Oh, well, it's difficult for me to answer because we don't build quantum hardware. So,
No,
so it
imagine if you
depends
had a
on
quantum hardware, I guess, would you have a customer willing to pay now? Or you expect in 3-4 years time or 10 years time? I don't know.
So it depends on the quality, right? Like if the quality is amazing, then of course there will be lots of customers. Like if the quality of the network. So for example, there are some use cases you were talking about, those alarm or even position verification, and also those high frequency trading things. If these things are matured, then of course you will have lots of customers and people will be ready to pay for those things. I mean, I think what from again end user point of view, it would be nice if we have already established quantum entanglement distribution network so that end users can use them just the way we use the classical internet rather than having our own private network. So
okay,
that's the
great. And Ravana?
Yeah, I would love to have dollars from our customers like yesterday, man. I mean, come on. Realistically, it all depends, right? So, people are making money with prototypes already because there's a ton of people out there wanting to get into the quantum revolution and trying to understand what it is that quantum can do for them. So we can sell if there is sufficient number of people who are just interested in experimentation. Whether it translates to downstream revenue or not really doesn't matter, right? You can actually find a customer who would just buy, for example, maybe if we place our entanglement chip, maybe there'll be enough people to just buy and experiment with it, right? Not that we have done that or there's an immediate exact roadmap around it. But my point is basically that may not be the a yardstick to measure quantum network penetration, because dollars exchange out of promise of the future and experimentation. What really matters is the end-to-end application. If there's an end-to-end value, and how much time does it take for us to drive that end-to-end value is really the key question, in my opinion. That I think is again dependent on the application, right? QKD already has a real end-to-end applications today. So in that sense, quantum network for a QKD like application is already there. Now, if you want to go beyond QKD, right? Like for example, the quantum alert that we talked about, that has the potential to maybe depending on again customers' interest, but that has the potential to come out in the next maybe couple of years-ish.
Thank you.
Yeah, so I would say depends really on the type of application, but
Mahdi, very quickly, if you have.
Yeah, no, for very much similar to what Romana and Kushek said, with the difference for us that we already have sales and revenue, and our revenue is changing over time. When we started selling, we started with hardware. We used to sell the entanglement sources, the APC devices. Now this year, almost exclusively, except to our partners, we focus on selling the rack system. So we sell the Carina systems. And most people who come to us, these are global test beds. That doesn't necessarily mean it's a university or national lab. It could be a test bed by different telcos from around the world who themselves are very interested to have these technologies to work on use cases. So they don't need like 100 racks. They could live with 2 to 5 of these racks because they want to build a small test bed so they can test things on top of it. We are working on these use cases mostly because as a company, we're interested to move from selling 2 to 5 into selling 20 to 100 racks because people would buy 100 when you give them a use for them, obviously. So we're already doing good. And like, I feel like a place that could be actually based on at least the interest I see in the market. If you could find a way to build a very versatile network and put it on the net and the cloud for people to have access to it, to do use case development on it, rather than everyone has to build their own network, that could already be a very good source of like quantum network as a service for a telco or a quantum company.
Great. So I think the final question is very important. I guess we had lots of students attending. So the question is that do you need a PhD in quantum to be involved in quantum industry? So I go very quickly around the table. If you can, Ramana, do you want to answer that first?
yeah, so absolutely not, I would say. To be associated with quantum, I mean, we all work with abstractions. Do I know anything? Do I need to know anything about how a microprocessor works in order for me to be in computer science? I don't. I mean, it would be nice to know, but you know, we live with abstractions, and I think the quantum industry, once the abstractions are elevated sufficiently, there will be a need for more systems people, application developers, you know, all types of people to come into the quantum industry. So you don't need a PhD to be in a PhD in quantum to be in the quantum industry.
Okay, thank you. Kaushik?
Yeah, I agree with Mona. Yeah, so I mean, there are certain tasks, of course, like if you want to be very much specialized in certain area, you need PhD. But like there are many areas like where we see like a gap between bringing like, and that gap it's very crucial. It's very crucial to fill up those gaps if we want to bring quantum technologies just from lab environment to real world applications. And those are mostly like engineering related tasks, and for those things you don't need PhD.
Markan and Mehdi, anything addition to that? Yeah.
Yes, I think it's like with many other raising technologies that probably you better spend the 4 years in getting something done than getting a PhD.
Yes. Good. Markan?
Yeah, I mean, I think that any industry needs people at all levels of background and skill to contribute to, and I think there's a lot of rewarding positions and jobs for people of different backgrounds to contribute to this technology for sure.
Mehdi?
Honestly, on my side, maybe this is a little bit more controversial, but as a startup founder who really cares about building quantum technologies, who lives a lab, I really care about limiting the percentage of PhDs we have, because otherwise we're just doing research. At QNEC right now, only 20% of us are PhD in physics. We actually have more of my team just came directly from their undergrad than they came from with their PhD. Most of the team is engineering and software background.
Oh, that's great. And Nick, final thought from your side?
Yeah, so I think that, you know, for us to make this technology a reality, there's a lot of non-technical challenges that need to be solved, right? And even among the technical challenges, I mean, there are very many different layers of the stack, right? So, you know, the PhDs are really good at doing certain things, but there are other things where, you know, for example, you need craft labor in order to do some of the things to make, you know, the dreams possible. So I think that there's a very broad scope of trainings and careers that are absolutely critical towards making this technology real.
Okay. With that, we are on time, and thanks for all the panelists and the speakers today. Again, big thank you from Ramona and myself and the whole Cisco team for helping us to have this great day today and contribute to the quantum as a whole. I am pleased to say that we had around 500 viewers for today, which is great. And thanks again for your contribution. The recording will be available in the Cisco website and Cisco YouTube channel and later dates.